Testing, testing.
Testing, testing. Hello, hello. At the Department of Computer and Information Science at the University of Pennsylvania. He was previously at Georgia Tech and Intel Labs in Berkeley. He has his PhD with Alex Hyken at Stanford and has also worked with Jens Palsberg in Purdue. And his research is at the intersection of PL and AI. And he has developed principles and practical approaches to neurosymbolic programming. He's wants to improve programmer productivity and software quality through AI-enabled programming tools. He has developed Scallop, which is a well-known neurosymbolic programming language and compiler toolchain that is freely available. And he has applied deep learning to program verification, program repair, program analysis, and program merging. And he's going to talk today to us about what's still missing in static analysis, a decade-long journey. So the floor is all yours, Major.
Thank you, Manuel. Yes. Okay, hope I'm loud enough for everyone to hear.
A brief history about how this came about. I gave an invited talk at SAS in 2019 in Porto, in Portugal. And I remember Kuso being in the audience there and being really scared about how I would come across. And now again, I got invited, and I hesitated to accept because I was dreading that he'll be here again, especially at a time where I've moved even further away from the classic style of static analysis. But nevertheless, it's nice to be among all of you who do great work in this field, and I'll show why it is even more, not less relevant in the age of AI. AI as in artificial intelligence. Okay, so this is joint work with two of my PhD students who will be graduating this year, and my postdoc, Saikat, who's a faculty now at Cornell, and is hiring students in this field. So if you are PhD students, so if you are prospective PhD students, please do apply. So here's the high-level structure of my talk. When I say static analysis, I actually mean statically analyzing program text rather than, say, a particular style of static analysis like abstract interpretation, right? And in fact, especially today, there are these three broad approaches. First is, of course, classical symbolic reasoning. Second is modern machine learning, and in particular, large language models. And finally, an integration of these two paradigms, which has been come to be known as neurosymbolic approaches. And here's how one might position these three approaches as a pendulum, right? So we see these states, 1 and 2, which are sort of the extreme symbolic and neural approaches, as sort of somewhat unstable states, whereas the equilibrium probably lies with combining these two approaches in a synergistic way. Okay? So I'm going to start with a problem which I actually didn't work much during my career, but I have gotten increasingly interested in it over time. So it is the problem of finding security vulnerabilities. It is like a grand challenge in our field, right? We all aspire to find a bug someday that would be named, would be given a CVE number and so on. And there's a reason why this is a grand challenge. There are now many bug bounty programs that actually give you pretty hefty monetary rewards if you find high-value security vulnerabilities. Um, uh, there was this Cyber Grand Challenge in 2016 by DARPA to try to automate the detection of security vulnerabilities using classical symbolic reasoning. And now DARPA is once again at it. This is an ongoing challenge called AI Cyber Challenge, where I hear none of the teams actually are using artificial intelligence. They're still using classical symbolic reasoning and a lot of manual effort. Okay, so how does one systematically approach this problem, right? So one solution that is well known in the field is called static taint analysis. In fact, even in this audience, I can see several who have built very general frameworks to target this particular problem. And the reason why this framework is interesting is that, first of all, many security vulnerabilities that can be actually viewed as instances of this framework. And they have been come to be known as CWEs, or the Common Weakness Enumeration. And I've listed some of them here, which is OS command injection, cross-site scripting, and so on. There are well over, I think, 300 categories of these, which I'll show later today. And these are typically caused by simple programming mistakes, such as failing to check and sanitize user-controlled inputs. And as I was saying, static taint analysis is this general framework to express rules to detect common security vulnerabilities in programs, right? And once again, when I say static taint analysis or the word rules, I mean this in a very general sense. One could even imagine a large language model as following certain rules, for instance. So here's a running example that I'll use throughout my talk. This is a known vulnerability in a Java library for cron data manipulation. So let's look at how this vulnerability works. It's a code injection vulnerability that begins with what is called an untrusted source. This is a function which, say, a user whose input a user can control, right? In this case, it's the isValid function where the argument value can be tainted, okay? And we see that it flows to the parse function. So the user can feed an input string here, which is now parsed without sanitization. And the parse function here might actually throw an error because of a malformed input, which in then turn gets handled back in this isValid function, which then tries to parse this string as a Java, using Java expression language as an expression. And so now a malicious user can feed in an input string, which could involve, say, running a malicious command, for example, deleting all files on the server side. Right? Okay, so let us look at how a symbolic reasoning-based static analysis might perform on this CV, right? So as I said, has been the dominant approach for much of the history of static analysis. And it underlies many tools that are very widely used today. I've just listed a few of these here, but there are many others. So the one that I'm going to use the most in my talk today is something called CodeQL, which started as part of a company called Semel at Oxford University and is now part of GitHub. But there are many others. Facebook, for example, has its own Facebook Infer, there's SNCC code, and so on. Right? And I think this community here has a lot to be proud of. It has come a really long way. I've just listed some success stories. The first is actually from Semel itself, called variant analysis, where if you find a certain vulnerability in a large code base, you might want to write a precise static checker to find other instances of the same vulnerability. And there are well-studied reasons why a variant analysis is needed. The way programmers think is very similar, and so even different programmers might create the same kind of security bug. But also, we now have really robust checkers for many different CWE categories that I will show shortly. And these are even integrated into continuous integration and continuous delivery pipelines at many of the top companies in big tech, such as Google and Microsoft and Amazon and Facebook and so on. Right? But on the flip side, right, one wonders why hasn't this problem been solved, right? In 2023 alone, there were 29,000 CVEs that were reported. And this was actually even higher, more than 4,000 higher than in 2022, right? One can look at a program which one would expect to be very heavily studied by security analysts, right? OpenSSL. Many of you might even remember the very famous Heartbleed vulnerability here, right? So this is a program that is extremely heavily scrutinized by static analysis and fuzzing and so on, right? And yet we still find trivial buffer overflow vulnerabilities in this program, right? And actually, a few years ago, Microsoft had this study which showed that over 70% of vulnerabilities in their code base are still well understood memory safety issues. There are other issues here, which is whether the programming languages are the right ones and so on. But the broader point is still the same, that despite very impressive advances in symbolic reasoning, these bugs persist. Right? Okay, so I talked about one particular CVE today so far. But let's actually take a more broad look at one of these tools, which is CodeQL. So today, CodeQL has a pretty robust data flow analysis engine, which is interprocedural. It actually can take several minutes or even hours on a code base that has more than 1 million lines of code. It's really well engineered. And now with this single framework of global data flow analysis, one can instantiate a lot of different static checkers, right? In fact, there are over 4,500 such checkers spanning 300 classes of CWEs. And I've shown you here the breakdown of these checkers, both by CWE on the left and by the programming language on the right. So let us look more deeply into how a static, a symbolic reasoning engine like CodeQL actually works. So CodeQL works at the level of an entire repository. And while this might seem obvious to people in this audience, when I'll go to large language models, this actually will become a drawback because they have a very fixed context width, right? So it is impressive that a tool like CodeQL can simply take in an enormous repository as input. And what it does is constructs an intermediate representation of this program, which is essentially a relational database, right? And this process can, again, take several minutes or even hours for a very large code base. But once this process is done, you now have this database, which is a faithful representation of the original program. And so now you can run all your checkers on that database, pretty much like SQL queries. And I've shown the simplest such query here. It's in fact a template for static taint analysis, where what you see here is the function flow path, which essentially performs this global data flow analysis to find some code path in the input repository from some source to some sink without going through any sanitizer, right? And now, as you can imagine, this template can be instantiated to many, many different checkers simply by overriding how sources, sinks, and sanitizers are defined, okay? So today, I'm not going to go into the internals of how to program something like a global data flow analysis. But it suffices to say that decades of research has gone into building something like this, right? And now out comes this a bunch of potential alarms, right, that you can step through. And I say they're potential alarms because these might be false, right? In fact, a tool like CodeQL has both false positives and false negatives. So it might also miss bugs, okay? And in fact, lo and behold, CodeQL does miss the bug that I started out with today, right, in cron utils. And let's see why, right? So the reason is pretty simple, actually. CodeQL is missing specifications of these sources, sinks, and sanitizers, right? And you might wonder, is it something that can be done easily, right? And the answer is no. There are actually thousands of unknown APIs in these large projects. And in fact, CodeQL does have many manually curated specifications. Since we are looking at Java here, they've done this across 360 popular Java library modules. But this is not a one-time effort. These libraries are evolving, and so they have to be maintained over time, right? In case you're wondering what such a specification looks like, in particular for the CV that I showed you in cron utils, even specifying something as simple as a source or a sink involves a very nuanced analysis of the code and an understanding of the APIs, right? So in this case, I'm showing you one specification of an untrusted source, which is the isValid method, whose parameter 0 can be controlled by a malicious user. And what you see next is an example of a sink specification, which was the function that parses the input as an expression, as a Java expression. Okay. Okay, so now in general, let's take a step back and see what are the challenges for symbolic reasoning. The first, as I just mentioned, is false negatives due to missing specifications, right? And of course, CodeQL might have false negatives for many other reasons, but for today, I'm just going to focus on missing specifications as the reason. But there's also another problem. I haven't shown you the false positive rate of a tool like CodeQL. It is actually pretty high, and I'll show you numbers later. It's well above 80% false positives, right? So, and why is that? Because symbolic reasoning tools can get too caught up in the low-level details and lose the bigger picture, which we call the contextual information, right? And so both of these actually significantly increase the burden on developers to the point that these tools can even become unusable. Okay. So let us actually see how bad this is in practice, right? So when we set out to do this study, we realized that there weren't any high quality benchmarks out there, right, of labeled vulnerabilities. And so we set out to curate our own, which is now publicly available, called CWE Bench Java. And although we have done it for only one language, Java, and for only a few CWE categories, it is an extensible benchmark that you can easily extend to many other languages and CWE categories. So you get a sense of how much effort goes into creating a benchmark like this. We wanted a benchmark that is real world, so that has extremely large and widely used projects, that is also compilable so that we can run static, traditional symbolic reasoning tools on it. We'd also like accurate labels of the locations of vulnerabilities and their fixes, and so on. So as you see here, even though we start with casting a pretty wide net of over 1,000 known CVEs, which we get from GitHub advisory databases, the final number came down to just 120. But what is nice about these final set of vulnerabilities is that it is highly curated, right? So even the location of the sink of every vulnerability here was manually inspected. And we only looked at 4 CWE categories just because of the amount of manual effort that can go in here. So here's some statistics of this benchmark. So as I said, there are 4 CWE categories for a total of 120 vulnerabilities over 78 Java projects. And the average size of this project is 300,000 lines of code, with the largest being 7 million. And now we are ready to see how CodeQL does on these vulnerabilities out of the box. Right, turns out actually it has a pretty low recall, right? So it only finds 27 out of these 120 bugs, known bugs, right? And one can ask, what about other tools? And we ran a few of them. Again, these are best effort experiments. I could imagine that you could put in some effort, and if you had some expertise, more expertise than us in these tools, I'd be more than happy to hear if you can give me better numbers for these tools, right? But I wouldn't be surprised if it's still in the same ballpark that you see here, right? And so this is, in some senses, clearly a negative result, right? That despite all of this engineering and research that we have put in these tools, that for our hardest and most pressing problem of security vulnerabilities, the state of the art is pretty bad in practice. So now let me switch gears to the next category of approaches, which is deep learning. But before that, let me just pause and see if there are any questions. Yes, Francesco. We haven't. Actually, I have one comment about this. And it again is a very small sample size. I think security researchers don't even understand how to use or extend a tool like CodeQL. I think the declarative nature and so on is, yes. That perfectly, aligns with what I too heard. Yes. Sounds good. S- Sounds good. Yes. Yeah. 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 Our future work is certainly to get also, a benchmark like this for C. And, yes, and that point we will be happy to, evaluate. Sounds good. Okay, thank you. Yes, sounds good. Okay, anything else before I proceed? Great. Okay, so let's move on to deep learning. I initially wanted to speak about various machine learning approaches, including probabilistic graphical models and so on, that dominated a decade ago. But I decided to skip directly to large language models, and I'll actually tell you why. Right. So a quick preview for those here who might not know what a large language model is or how it works. It's essentially a neural network that simply produces a probability distribution over a finite vocabulary of words or tokens, right? Given a finite input sequence of words from the same vocabulary. That is all that it is, right? So here's a quick illustration. You give as input a sequence of tokens, right? And you get as output a probability distribution over all the tokens or words in the vocabulary, which is fixed. And there are various ways to decode this. And so you can use greedy decoding, which would simply pick the word that has the highest probability in this distribution. But there are many other approaches as well, like beam search and top K sampling and so on. And this is what is called an autoregressive or causal model. What that simply means is that it happens one word at a time. and the probability distribution of the following word is dependent on the previously generated word, right? So this is an inherently sort of sequential process. You cannot produce the next word until you have produced the previous word. But the nice thing you have here is a remarkably simple architecture, which is called sequence to sequence. You give as input a sequence of words, and you get as output a sequence of words. Okay, that's all. Now, if we were just talking about all the rich sort of literature and guarantees that symbolic reasoning gives us, right? Why should we even believe that a model like this can help with code reasoning, right? I'll give you my thoughts, and I'll be happy to hear others. First is, even well before large language models came around, right? This is more than a decade ago now. Some researchers in software engineering sort of saw this coming, right? And they published a paper which at that time was somewhat controversial, which is called The Naturalness of Software, right? And here's a nice quote from it, which says that even though the programming languages are in theory very rich and complex, but the programs that people actually write are fairly simple and have repetitive patterns that should be easy to uh, um, leverage by what were then called statistical language models rather than large language models for various software engineering tasks, right? I have another reason why I believe they are good, and that is that it goes back to this very nice lesson by one of the pioneers of reinforcement learning named Rich Sutton. It is called the bitter lesson. This is primarily for folks working in the field of artificial intelligence, where Rich actually gives lots of examples throughout the history of that field where every time researchers tried to provide too much structure to solving problems, whether that is a strategy game like chess or it is something else, say object detection and so on, those methods were quickly rendered obsolete over time by methods that had less structure. And so the big lesson here, which has at least so far withstood the test of time, is that we as researchers should only build in what are called meta methods, right? That enable to scale with increased computation. And in particular, even as this available computation becomes very great, right? And we see this trend today, right? If you see how compute is growing, the biggest challenge for even large language models is where is our next scalability bottleneck that we should remove, right, to take advantage of this extra compute, okay? Here is another illustration of this phenomenon that approaches that at smaller scales, where smaller scale could mean the model size or the available data or the available compute, right? At smaller scales, it might look like your method is doing better for some notion of performance. And this is what is happening in the field of deep learning right now. Much of the papers that you see published fall in that category, that appear to be doing better today. But in a few more months or years, it will turn out that the simpler methods, okay, which were not looking as well at smaller scale, turn out to be actually much better as with scale, right? Okay, so let me show you an example of this phenomenon, which is called emergent abilities of large language models. There's this paper which was published a couple of years ago, which defines emergence as this property when quantitative changes in a system result in qualitative changes in behavior, right? And so we say an ability is emergent if it is not present in smaller models, but it is present in larger models. Now, the reason I'm telling you all this is I'll actually show you examples later in my talk where smaller LLMs will do much worse on security vulnerability detection or even sub-problems in that problem compared to much larger LLMs, right? So you don't have to necessarily go to see examples of this phenomenon outside our field. Okay, so here's one example, which is if you use specialized prompting or fine-tuning methods, such as chain of thought, right? Then these were observed to be emergent. I'll again show a concrete example for security vulnerabilities, where I'll show you the impact of chain of thought later today. And indeed, the smaller models, if you see in all of these charts, for different challenging tasks that were given specialized prompts like chain of thought prompting, the smaller models do very badly. But as you scale these models, as they get larger and larger, you see a spike in their performance, right? So indeed, quantitative changes in these systems result in qualitative changes in behavior. Okay? Here's another way to look at this, which I really like, from Hyung-Won Chung at OpenAI. So on the x-axis, you see amount of compute, and on the y-axis, again, some abstract notion of performance. Now, in the beginning, towards the far left, you see an approach with more structure winning over a one with less structure. But over time, as compute grows, the approach with more structure saturates, but the one with less structure keeps doing better, right? But then the question becomes, should we build approaches with even less structure, right? Could they be even more scalable? Okay. And now comes a very interesting observation. The answer is not necessarily. It really depends on where we are on the x-axis today, right? And in particular, if we are here, right here, okay, then actually it doesn't make sense for us to build an approach with even less structure, right? But we should remember to undo any structure that we put in for today, in case more compute becomes available tomorrow, right? So when I reflect on all of my research now, right, which had a lot of structure in it and was published in many of these conferences, I still feel good about it because at that time, right, it was the right thing to do, right? But if we were to do this today, one should be more aware of where we are on this scale, okay? Okay, so let us see how LLMs are doing on code-related tasks. So we know that they do great on code completion, automated program repair, test generation, fault localization, and so on. I'm just going to show you two specific examples that are leaderboards that are measuring where LLMs stand on these problems. So one is called Big Code Bench, which is essentially assessing what is called function level code generation. So can LLMs understand small pieces of code and do tasks such as repair and completion? And at the other extreme is the SWE bench, which is essentially about taking entire code repositories of projects and and automatically resolving issues, right? And right now, the accuracy is really low for LLMs or agent frameworks and so on this task, but we wouldn't be surprised if in a few months or years they would do as well on these problems as too, right? So what we set out to ask about a year ago then is, LLMs have been applied to all of these simpler code-related problems. Can they be used to statically detect security vulnerabilities? And we have this archive paper, which actually does a pretty comprehensive evaluation of where they stand, right? And here's a chart showing, a bird's eye view of how comprehensive our study is. So we mostly target C, C++, and Java. And we collected 5,000 samples, 1,000 from each of 5 different data sets that I'll show you shortly. And we compared against classic static analysis tools, traditional deep learning tools, and so on, right? I'm going to go into more details of each of these shortly. So as I was saying, we collected 5,000 samples, and these are balanced, so there's 50% vulnerabilities and 50% benign alerts here, right? And we took 1,000 each at random from 5 data sets across C++ and Java. And I believe 3 of these are synthetic. The first 3, Juliet and OWASP, are synthetic, and CV fixes is real world. Okay? And we constructed these 5 different prompting strategies. And our best performing prompt is actually one that asks the LLM to mimic the behavior of a data flow analysis, and in particular, a static taint analysis. So it's a very elaborate prompt which essentially asks the LLM to first list the untrusted sources and the sensitive sinks and any sanitizers before it produces a verdict of the vulnerability, right? We also give it the CWE class because that has a lot of information necessary to be accurate. Okay. So what did we find from this study, right? So first of all, we were actually expecting it to do much better than our traditional symbolic reasoning tools, but turns out that LLMs do pretty poorly, even the state-of-the-art LLMs. I believe we ran 16 different ones, including GPT-4 and Llama 3.1, 70 billion. But it turns out that their accuracy is barely above a coin flip, barely above random. So if you see the line, you see here that's a random guess, and LLMs are barely above that line. And if you perturb these programs with semantics preserving transformations, such as dead code insertion or variable renaming, then the accuracy further drops, right? So you see so lower means worse. But you do see that the larger models like GPT-4 get less confused by these patterns, right? So these are what are called adversarial attacks in that literature. So clearly, even LLMs alone aren't there yet for finding security vulnerabilities statically, right? So let me conclude this study. So first of all, we saw that LLMs across many different scales and families only have modest effectiveness in end-to-end reasoning about vulnerabilities. And the average accuracy was just 62.8% across these 5 data sets. And the highest, in fact, was 76% accuracy by Llama 70 billion with our data flow prompt. But it was on a synthetic data set, right? We don't even know if these LLMs are contaminated by these data sets out there, right? And indeed, the accuracies are about 10.5 percentage points higher for synthetic samples as opposed to real world, okay? So even this number, which I'm showing you of 62.8% is inflated, right? Because 3 out of our 5 data sets are synthetic. Great question. So thanks for reminding me. So these are, so we were limited to functions that are, that fit in the context of the LLM. So they were single file. It is balanced. And we, by the way, took care to remove comments from, say, the Juliet suite, which said there's a dangerous pointer dereference here and so on. Okay, so a lot of care went into it, yeah. Yes, the ground truth. So I will show you unknown bugs later, but we did, so this is a big issue in this field, which is the labels are noisy. And this is why we are limited to 5,000 samples. It's again a best effort that we curated as much as we could, but I don't think I think we just trusted the Juliet labels, okay? The real world ones are much noisier, like CV fixes, and that is where we put in more manual effort, okay? But here's the thing, there are a few silver linings here, and I need to speed up a bit now. So what we did notice, though, is despite this disappointing result with LLMs, they actually had two strengths, which are exactly the challenges for symbolic reasoning. The first is spec inference. Here's an example of a code snippet which is fed to GPT-4, and it correctly identifies the untrusted source function and the sensitive sink function, and even gives the correct explanation for why it is a real bug, which, by the way, CodeQL does not detect, right? So what we discovered from this study, right, is that there's a silver lining that LLMs might actually be able to improve both the false positive and false negative limitations of symbolic reasoning. And the way to eliminate or reduce false negatives is to provide these missing specifications to symbolic reasoning tools. And the way to reduce false positives is to use LLMs to do contextual analysis, right? So there was also another silver lining that we observed, which is we asked for all of these LLMs across uh, all of the CWE categories that we looked at, was there any correlation, right? As in, were certain LLMs doing really well across the board, or were there certain CWE categories that LLMs were particularly good at? And indeed, they are good at CWEs, which just require local reasoning, okay? And I've highlighted a few of these here, from command injection to out-of-bound reads and writes and so on. And you see these by the shading here. So there are certain categories where LLMs are better, right? Okay, so now I'm going to finally switch gears to the most interesting to me of these three kinds, which is neurosymbolic approaches, right? Which is combining the best of both of these. Some of you may have heard this intuition for why neurosymbolic approaches could be the future. This is a book that was written in 2011 by noted psychologist and economics Nobel laureate Daniel Kahneman, called Thinking Fast and Slow, right? So he called these system 1 and system 2, right? So you can think of system 1 as something like GPT-4, which is fast, right? It operates automatically and quickly with little or no effort. Whereas you can imagine our symbolic reasoning tools like CodeQL as system 2, right? Which involve a lot of complex computation, okay? And here are some examples where even we, the way the human mind works, you can relate that there's certain things we do instinctively, such as 2 plus 2, whereas others, such as solving 17 times 24, might involve using an algorithm with a series of steps, right? And so what I'm going to show you next is a tool that we have built, which is based on this neurosymbolic approach that puts together the best of both of these paradigms, right? And we have this paper as well on arXiv. So we call it Iris. It takes a whole repository, as someone was asking, this is now no longer limited to single functions or single files. We are back to the world of symbolic reasoning, where we can process hundreds of thousands of millions of lines of code. And it produces as output both a static path, a witness, but also an explanation, right? So how does Iris work? So here are the key ideas, right? There are two of them. The first, as I mentioned, was to overcome the limitation of false negatives that we have in tools like CodeQL, right? And we can use LLMs because they have this inherent knowledge of which APIs could be, sources or sinks or sanitizers, right? So we still use CodeQL to extract all of the potential candidates for these specifications, and then we use simply few short LLM prompting to get the source, sink, and sanitizer labels, right? The second key idea is to provide contextual analysis. So once again, LLMs can look at a static analysis report and use a lot of auxiliary signals, which I'm showing over here, to give a verdict whether it is a real bug or not. If you see this prompt, once again, it is very carefully crafted. Okay, so it's actually a prompt template that I've instantiated on the running example that I showed you at the beginning of my talk. And when an LLM sees this in its input, it gets a lot of auxiliary signals. For example, it knows that we are looking at a code injection vulnerability. It also knows that this is the source and that this is the sink. And furthermore, what is the context around the source, the context around the sink, and even some of the crucial steps that a symbolic reasoning tool like CodeQL could have produced, right? And a lot of engineering has gone into curating this so that it just fits into the context of an LLM, right? So imagine if a code path is extremely long, how do you decide which functions are interesting to show, right? Um, so in this case, the LLM rightly concludes that in our example, there is a vulnerability and gives this nice explanation that will save a developer time, right? And here's the entire pipeline. So we have these 4 stages, which I'm going to just go a little bit fast over. So the first stage is where symbolic reasoning is used to extract candidates for specifications. Stage 2 is where an LLM will label them. Stage 3 is where we go back to symbolic reasoning to now run our static taint analysis. And finally, the last stage is where each of these alarms are inspected by the LLM for giving a final verdict with explanation. Okay, so that was a lot of description about Iris. Let's actually see how it performs on CWE Bench Java. Okay. So remember, CodeQL could only detect 27 out of the 120 vulnerabilities that we had, right? So turns out that all of the, if you take any reasonable large language model and integrate it into Iris, we get a dramatic jump in the recall, right? I've also shown you the false discovery rate here. It is really high, so there's much work to be done there. We do bring it down somewhat, right? Um, so is, that is good news, which is we at least improved the recall. Um, One can also ask how well does this contextual analysis do in terms of precision, right? So notice again, there's a lot of information being given to the LLM. Once we apply this, it turns out that the larger LLMs are significantly better at eliminating false alarms as compared to the smaller LLMs, okay? Actually, the smaller LLMs, if you see this Llama 8 billion and this DeepSeek Coder 7 billion, they err on the side of thinking things are vulnerable when in fact they are not, okay? So they don't help with false positives. But as you go to larger models such as 70 billion and who knows how big GPT 3.5 and 4 are, but they do a much better job at eliminating false alarms, okay? So this again goes back to emergent phenomena that larger models actually can be better at these tasks. There was also a question about whether we found new bugs. We did find many new bugs actually, but there are many other problems with triaging a vulnerability, right? One has to tell whether it is exploitable and so on. We're just solving a small piece of the bigger puzzle here. Okay, nevertheless, we did find 6 bugs that we thought were exploitable and not previously known. And here's actually our tool, which we plan to open source. It has a nice IDE that you can use. This one is showing the report for the cron util vulnerability that I showed you earlier. So it shows different code paths that CodeQL found, along with explanations that that GPT was able to provide. Okay. Okay. So in the last 10 minutes, I would like to very briefly touch up upon this was just one instantiation of neurosymbolic. Can we build a general language and compiler, right? it turns out that actually, if you think of large language models, conceptually, they're really simple. They're simply stateless functions, which can be viewed as, which one can integrate into symbolic reasoning tools using a relational interface. And in fact, the reason we use CodeQL is much of my research works with relational programming and data log and so on. And so we found it especially easy to integrate LLMs with a tool like CodeQL, which also works with relational databases. So over here, so we do have our own language and compiler called Scallop, in which you can actually write things like this. So you can invoke any LLM, in this case GPT, and extract a bunch of relations out of it. So you see there are bound and free variables for each of these relations. What that means is you can feed in a program snippet, that is the bound argument, and you can get from it you know, data flow edges or sources or sanitizers or sinks and so on, right? And now you can feed in an entire program or code snippet and get this tabular data uh, out of this LLM. And once we have these relations, now we know how to use classical symbolic reasoning tools, right? And here, what I've shown you is a simple program that computes the transitive closure of a graph whose edges are given and then finds vulnerabilities, which are essentially paths from a given source to a given sink without going through any sanitizer. Okay? Um, Great. How does this perform? We have just run this on a tiny data set, which is OWASP. This is a synthetic data set. But you see, even this simple integration of a large language model with a classical symbolic reasoning approach immediately gives you extremely high accuracy, 77% over here. Compared to just CodeQL, which is at 63%, or just an LLM, which is at 64%, even if you use chain of thought, which brings it up to 67%. Okay? I'm going to very briefly tell you about what we can do beyond static analysis, because I think we as researchers in programming languages have a lot to contribute even to the rest of artificial intelligence, right, which works with vision and natural language processing and so on. But again, in the interest of time, I'm just going to breeze through just two applications. This is what is called a knowledge extraction. You know, you have a passage here, and there's a question asking about how two people in the passage are related. It's a classification problem, around a 32-way classification problem, right? And the way a human would solve this problem is build this graph in your mind or on paper, and then you would work out based on certain logic rules of kinship relationships, right? Actually, it turns out this kinship problem goes back to even early work by Hinton and others. So it is actually a very interesting problem for neurosymbolic AI. So it turns out here the answer should be Nice. And the way we solve it using Scallop is pretty simple. Once again, we use an LLM. It turns out there's an enormous like diversity in the way passages can be written, even if these passages are generated by logic rules. Okay, and so you want to use a large language model to extract at least the basic kinship relationships mentioned in the passage. But you don't want the LLM to do longer range or multi-hop reasoning once those basic relationships are known. This is just like the transitive closure I was showing you for taint analysis, right? So actually the kinship relation is recursively defined, okay? And finally, you can get the answer that we expected, right? How does this perform? If you look again at purely neural approaches, they do much worse than the neurosymbolic approach I showed you. And as an example of the scaling laws that I mentioned earlier, 2 years ago, before LLMs were even there, we fine-tuned much smaller models like Roberta. And today, with GPT-4, we don't even need fine-tuning. It just works with zero-shot prompting, right? So a nice lesson here is that GPT-4, even though has scaled to use much more compute than Roberta, we are still giving some structure to this problem, right? And the structure is over here in these logic rules, right? But maybe a few years from now, even that structure is not needed, right? But at least today it is needed, as you can see from these numbers. We also work with other domains that I'm not going to talk about. This is multimodal applications. It's a pretty hot topic in AI right now. But the same basic principles apply. And what's actually happening under the hood in Scallop is probabilistic reasoning. It's not just discrete reasoning the way CodeQL does, right? So actually you can even, if a large language model gives you certain probabilities, you can propagate them through these rules using very elegant research that was developed in the database community called provenance semirings, right? So even though these rules look deterministic and discrete, under the hood, they are tagged with information which can be as simple as probabilities to as complex as entire proofs of reasoning, right? And I have just two more slides to tell you. This was all about prompting today, right? There was no fine-tuning or training involved. Um, but one can ask, is there, could one even go beyond probabilistic reasoning and do differentiable reasoning, right? And train these models along with symbolic reasoning components. And yes, we do have work. This was at PLDI 2023 that you can use. Why would you need it? Actually, if you see this architecture of Iris, turns out that many of the source sensing specifications it infers are wrong, right? It's remarkable that it still does better than CodeQL, okay? But it also tells you there's a lot of room to improve, right? Because these prompts are unreliable. And we did measure the precision and the recall of the specs that the LLMs inferred for Iris, right? And you see they're not perfect. For example, we measured recall against manual specs in CodeQL. We also measured precision for a randomly sampled set of specs that the LLMs inferred. And while GPT-4 does much better than the rest, there's still a lot of room for improvement, right? And one could wonder, how does one get that improvement? Well, strong supervision is hard. This was the whole point of this talk, that developers cannot keep maintaining these annotations, right? What Scallop allows you to do is to use weak supervision, which is sometimes also called algorithmic supervision. And the supervision here is only on the final output, or what is called the observable output, right? And why is this interesting? Well, because just like security experts don't have time to label everything in the intermediate result, but also in other domains such as doctors, right, or other specialists like lawyers, also don't have time to give very fine-grained feedback on a given large input data set, right? And so we have developed this approach to work simply with weak supervision, but I'm not going to go into the underlying challenges, which you can read more in Scallop. So I'll end here. Thank you all for your attention, and I'll be happy to take questions offline. Exactly. So this is the whole point in neurosymbolic, that we believe neural models should just be used for low-level perception and semantic parsing and things like that, but not. So the lesser burden you give to the neural models. But in your case, one would imagine a database that has information about your birth date rather than just hallucinating, right? Or your database of your publications. So you would write that symbolically, um, right? But you would use, a large language model only to do very basic things like semantic parsing that I showed earlier over here. We can talk more offline, but I'm not saying we eliminate the problems, but we reduce them as you put in more symbolic reasoning. Thank you very much. Sorry for eating in heat.
Hi. So, um, I'm Pankaj. I'm a PhD student at IIT Kanpur, India. And today I'll talk about application of program synthesis in generating abstract transformers and transformers for reduced product domains. This work is with my supervisor, Subhajit Roy from Kanpur, and Tom Raps. So I'll start with a simple program and we'll see why we need abstract transformers. So the first line takes an input. We are using interval domain in this case. So minus infinity to infinity because of assumption it becomes 0 to infinity, and since as the c is less than 10, then we get there. So now we know how to do addition in concrete. Okay, but now we have to know how to do addition in interval. So that's where this notion of abstract transformers come. So now we are doing addition of intervals. So we know that lower limit of interval will be addition of lower limits and same as higher limit. So with that, the main point here is that for every concrete operations, we have to create these abstract transformers. Though at line number 5, there is also, we have to create the transformer, but we thought, let's not go there. Addition will work fine. Okay, then we continue, and this will reach the fixed point, and we end up at line 10, and now we know the assertion will not be violated. Okay. We prove that assertion will not be violated using interval domain. Okay, so nobody knows this, so I'm just putting this slide because putting abstract interpretation slide in SAS stupid. But still, for the completion, there's alpha to get concrete to abstract, the gamma from abstract to concrete, and there's a beta which takes a single element of concrete domain and it maps to an abstract value. Now, what is the abstract transformer? So you have a concrete domain, and there is an abstract transformer for concrete domain, and we have to create an abstract transformer in, the transformer in concrete domain, and we need to create an abstract transformer for abstract domain. It's tricky, even for trivial operation and trivial domains, and we have found that these are the manually written codes are error prone. Okay, the problem statement, let me first come up with the problem statement which says that, can you automatically get that without ChatGPT? So given the formalism point is this, so we have a concrete semantics of the concrete transformer and the description of the abstract domain and their relations, alpha, beta, gamma, and a domain-specific language L. So since I'm talking about program synthesis, so program synthesis uses this notion of domain-specific language, which describes the string or programs, how the abstract transformer will look like. And our job is to find a best abstract transformer of F for given domain A in given language L. So if you see actually the best one can be, if you apply given a abstract value A, and if you apply f of c for each element contained in A, and you take beta and join it, that will be the best. But we want to create a tight over approximation of that because sometimes it's very hard because this gamma might get into infinity and all. So we built a tool called Amurt. So in Hindi, Amurt means abstract. So we built a tool called Amurt, and it was presented 2 years ago in UPSLA. So which solves this problem. So given a single domain, we try to, can we automatically synthesize these abstract transformers? So I'll take a couple of minutes to describe what we have done. Okay, then we'll see how we have extended this work to the current work that's in published in SAS. So the challenges are like, for transformer synthesis are like, it might not be computable. That the one we just saw, the best one, it might not be expressible in L. Okay, and there is a precision. There's a when you try to synthesize a best transformer, you can think of a like lattice of partial order of the precise transformer and make lattice and you try to search over there. Okay, so let's try to see the overview of the Amurt, which is published in UPSLA. So it uses some counterexample guided inductive synthesis. So it tries to meet two objectives like soundness and precision. And since two objectives, two type of example. first one is positive example. So you see the positive example is of type in the tuple of A C prime. So A is the input abstract value. C prime is the post concrete value. Not input C, it's a post C. So what it means, a positive example means that the C prime should be within the post A, right? If you apply this best one, then whatever the value you get, the C prime should be the post value of A. For this case, let's talk about increment. And if you take an input 5,9, so C prime 10 is always, the 10 will be always in the, if you apply best transformer to 5,9, 10 will be on that. Because if you see it becomes 6,10, so 10 is within that. So it's a positive example. Means we need, positive example means the transformers need to satisfy those examples. So something called negative example, which means that transformer no need to satisfy them. They are excluded. So we say there, assume there exists a best transformer expressible in L. So we see this C prime is not a part of that. The post A, C prime is not part of that. For example, 5,9, 2 is not a negative example because whatever you do, 2 will never come in the post image of 5,9. Okay? So these soundness and precisions are driven by these two type of examples, positive and negative. So overall, the overview of this algorithm is that there are two loops. One does precision check, another does soundness check. Soundness check generates positive counterexample. Precision check creates negative counterexample. And with this positive and negative example, we try to synthesize a function which contain positive example and refutes the negative example. It's not that, there are some tweaks. If I have time, I have slides for it, but you can see more in the paper, but not directly there. You need to be some changes are there. So just an illustration. So this, the dash one is the best. We want to over approximate, tight over approximate. So it's just an illustration how these things work. So we started with some. Then this positive example comes. We try to include that. So we expand it. Then we say, okay, this is a negative example. We're trying to shrink it. And so this positive and negative example plays a role while getting the tighter one. So negative says shrink, positive says expand, and they somehow may come up to a fixed point where you cannot do more shrinking, you cannot do more expanding. Then you stay there and you get the best one. In the first tool, the UPSLA one, we have claims that if the algorithm terminates, it's a best L transformer. And if the DSL, the language we provide for synthesis is finite, then the algorithm surely will terminate. Now let's come to this paper where we move in the UPSLA part, we did synthesize for single domain. Now we're moving from reduced product domains and how new challenges comes up when you do that. So for this, to explain the things, we have taken twice interval domains, odd and even. It's similar to interval domain, but the endpoints in odd interval domain, the endpoints are odd, and in even, the endpoints are even. So the product domain means so I'm trying to, so the notation I'll be using, so it takes odd and even, then you do that. So if you see, I'm putting an angular bracket saying that this is first element of the tuple is odd value, and the second is the even value, and the gamma of them will be the intersection of gamma of both. So let's see the transformer for increment in product domain. So it's a direct product domain, so it will be like individual transformers. You can do the product thing. So it will be left part will never be incremented in case of increment because odd will move it to even, which is not correct. You have to be in odd. And the right part will be increased by 2, not by 1. So you see there is some imprecision there. Imprecision is there. So can we do with reduce? So in this case, I'm trying to show what direct product transformers and reduced product transformers means. So in direct product transformers, the The middle line shows the transformers, and the top line says the input abstract values. So each transformers in direct product takes an abstract value for the particular domain of the same domain. But in case of reduce, it takes information from all over, from other domains value, and try to emit a precise abstract. Now, same example, I'm showing the um, direct product transformer. So the reduced product transformer comes out to be like this. So the odd interval, the left part, it is using even part, not a single element from odd, and it's incrementing by 1, and the even part taking the odd. So we assume, well, this ONE are like we apply reduction on top of that, so there is the minimally minimally representable odd and even values. So, so this is a sound and precise transformers. And if you see, so for the same input, so the gamma of this will becomes from 5 to 8, but this gamma will becomes 6 to 7, which is more precise for increment for a given same input abstract value. Okay, so it shows the reduction helps in getting the precision. And by the way, this is synthesized by our tool. Now, let's visit the problem statement. We have seen this problem statement. It is the problem statement from our earlier paper. Now we move it to a reader. It changes the red part. So it's now a couple of abstract domains and their relations, the alphas for corresponding domains and betas, gammas, and the domain-specific language for each domains, because they might be expressed in very different way. And our job is to find a reduced transformer, which is a tuple of each transformer for each domain. Okay, that's why we build the AMUT2, which solves the above problem. Now, so we'll show why we not use the Uppsala part, why you need a SAS paper to do it. Okay, we just try to motivate why you need another paper to just do the reduced product domain, synthesis of reduced abstract product transformers, rather not use the earlier part. So there's a conversation between Mr. Penguin and Miss Owl. So the Penguin asks, why not use a mode? So it's only for one domain, right? But take the product domains of the multiple domains, take the product of them. Why can't a mode can do that? But problem is that will it scale? The scalability is the issue. Okay, so if we try it out and we found that for a given twice interval domains, odd and even, we try to synthesize addition using a mode. It took 10 hours. Till within 10 hours also, couldn't synthesize. Okay, fair enough. Now Penguin has no point on that. But what about synthesizing transformers independently using a mode? So let me take some time to explain this part, because it's a little bit of confusing. Why this is, what do you mean by independently using a mode? So when we do a product, when I do product domains and try to synthesize using a mode, what a mode was doing, it is synthesizing, okay, so this first line shows the increment for odd, and the second line shows the increment of even. It takes values from odd and even. So Amut was doing, try to synthesizing this odd and even all together. But what one can think, okay, why don't you independently synthesize? Take the odd domain, allow it to use the even values and synthesize, and take the even domain and then allow it to use the odd values and try to synthesize. So like you have a parallelly you're running a mood for the different domains and try to get it. Will it work? The problem is best of I plus best of k is not the best. So let me show you pictorially. So let's assume we are trying to abstract a circle using a square. So now in case if you want to abstract a circle and we're using product domain, you can use same two kind of square, same one pink and blue. So if you ask independently to do, okay, I ask Amut the first one to synthesize, to abstract it out, and the second one to synthesize, abstract it out. So you see the intersection will be like a same. There is no improvement in the precision. So if I do it independently without talking to each other, so what you have synthesized, what the other domain has synthesized, and can it improve based on the other domains transformers, can we improve or not? Without talking like that, if we do it, we might get something less precise. But if we do dependently, what it means by dependently means, first I synthesize this part, then I saw that, okay, the other guy synthesized like that, can we do it better? Such that the overall the preciseness increase. So you see, so if I have the DSL where square can rotate, so by rotating 45-degree angles, it creates more precise abstraction than the independent one. So that's why we need a neural algorithm where you can talk with different domains and the transformers it synthesize and keep on make it more precise and so on. So we have talked about the positive and negative example for a single domain. Let's talk about what will be the positive and negative examples for the multiple domains. So you see, so I have shown 3 domains, circle, triangle, and square. So the P1 is a positive example because it is included within all domains. But the N1, N2, and N3. So N1 is a positive example for circle, but not for other. N3 is for triangle, not for other two. So what we have, so now even the formulation changes. Now earlier was A, C prime, now it's become a tuple of A to N, comma C prime. Now the positive examples is shared because you take an intersection of that. So it has, every transformer has to contain all the positive examples, but negative examples are private. Because one negative example might be positive example for other. So when we say negative example means if one guy say I am refuting this guy, that's a negative example. But positive example means everyone has to include it. So that's the overall illustration of how our algorithm works. So if you see, you have 3 domains, and we put 3. So each domain, if you see this part, we have seen for the Amut part. So for each domain, we'll run it. We try to synthesize best and precise, but this global positive example set is shared among all n, and we'll be using this transformer. For our algorithm, we start with the direct product transformer. Then what we do, we first take the triangle domain, and we say, okay, I fix the other 2 transformers. Can I increase this transformer of this triangle? We take one domain, we fix the other 2. Can we make this current transformer more precise? Then it runs for these loops keep on running, and it's try to you synthesize at best sound and precise transformer. Then we move on to another domain. Now we fix the other 2. Now we see, then can we make it more precise by fixing the other 2 guys? And we keep on doing that, iterating one after another until we get a best transformer for all. Now we have introduced something called K precision. What it means that how many transformers will synthesize at a time. If you see, if you make, suppose there are n transformers and n domains, and we make it n precision, it means you are synthesizing all together, which is not scalable at all. So in our case, we showed in 1 precision in this example, and in our experiment also we used 1 precision. Means we synthesize one single domain, transformer for single domain, and fix the other, and we keep on rotating for all the domains until we get best transformer for all domains. Our conjecture is that K precision can be weaker than K plus 1. Because if you see, we are trying to improve one guy by fixing the others. We assume that if we try to improve all together, we might get better solution. So we don't have a proof and we don't have a counterexample because in our experiments, we never found with 1 precision, we got the best precise transform. Yes, yes. Yes, yes. So means we could. So what I'm trying to say is that it is true, but we we couldn't find like proof like if I do it, means our experiments and all, we couldn't say that if I do one at a time and if I did three at a time, we get the same things. We couldn't prove like. Yeah, means you will be happy. Yeah, that's why we put a conjecture. If you give an counterexample, you will be happy to see, okay. Because we are taking, anyway, we are not means we are taking a step back. We say we are not good. So if you do that, we'll be happy. We make it conjecture to prove that this guy. Yes, I mean, we couldn't find that, that's why we put it in the conjecture, yes. So what claims we made, okay? If the algorithm terminates, we get a sound transformers. And we will be always one precision because we did one precise. And the theorem 5 says though our DSLs are finite, unlike the first work, Amur, algorithm might not terminate. So we couldn't, so what happened is that our algorithm works on in a fixed point of every domain. We get a precise and best transformer for every domain. So we couldn't come up with a proof that we'll kind of get a ranking function so that it always monetarily increase or decrease so that we'll come to a halting thing. So, but in our experiments, we never faced this issue. Okay, so what we have done experiments on, so you use two domains from string. So this SAFE STR is a abstract interpretation tool for JavaScript. It uses string domains to verify the JavaScript programs. And we have some 6 operation, concat, contents, tool, or. Yeah. Then we found that some are manually, synthesized one are manually better than the manually written one. So for like to show one example, so this something called SSK domains. What it does is that it keeps track of k strings at a time, and if the string size get more than k, it becomes top. Okay, and something called NO domain, simple, number or other, whether the string is a number or whether it's other string. But keep in mind, this NaN is a number, and it keeps lots of issue because of this guy. Means so this is the this NO domain is already defined already. It's a no. Yeah. It's number or okay. I think this will make more sense. It's either number string or it's an other. All are string in JavaScript, but NaN is like a number, not a other string. So if you do n concat an, it becomes number. Yeah, that's the problem here. So this is the save domain. So what we have found is, let me take one example. It's trim domain, a trim operation in save. So in the left part is the manually written one, and the right part is the we have synthesized. So if you see what it does is that first it checks at line number 3, and the left part is that whether the SSK part is top or not, means there are finite number of strings present or not. If it is, then you apply trim on every string and take the alpha of it, right? And after it doesn't do anything on this number and domain. So what is the line 9 says that if it's other string, it makes a top for this part, okay? But in synthesis, we found that if you use this, after trimming for each operation, if we do alpha of number also, we get a better results. And if you see, in case of manual written, we get a, if we assume SSK is 1, means one string, we get a number string for synthesized one, and then we get top for the manual one. And in this case, when there's a join, and if we use 1k, SSK is 1. So in joining, though the SSK part gets top, we can say more about the thing is that the number string using the other domain. But in case of manual, we can't say anything. So that's where we find the precision. So we found that it's not very trivial to get the transformers right, even in case of reduced domains. And whatever we have synthesized, we are equivalent or precise than what you have seen in the manual code. So before concluding, I would like to acknowledge the wonderful SAS reviewers because it made our paper better in many ways. And Intel, Research Science Foundation for IIT Kanpur, and CIPLAN Tech Funding to let me present this work in front of all of you. With that, I'd like to, and open for question. So this is an extended version. Uh, what we have submitted is a 40-page paper, then we have to reduce the paper. So whatever is a preprint is a reduced version of the paper which synthesized reduced abstract transformer. So I'm open for question if you have.
Thank you. So, am I correct in thinking that your both the previous algorithm, the current one, doesn't have any sort of monotonicity of the transformer? Because it seemed like your condition was that L was finite, not that there was some sort of finite chain in your language or something, right?
Finite chain in case of language means?
So,
Like-
so I guess I was wondering whether in your algorithm, whether you strictly increase the number of positive examples that you.
Oh yes, we keep on
and you-
collecting. We keep on, the positive example and negative example sets always increase.
So then why is it just the finiteness of the language and not like
Okay,
some sort of.
okay. You see, I've seen some more details in the paper. So we use some max set. Okay, let me show you if you don't mind. So something happens. So there is a negative point, this one, and if something positive comes, then we have to delete this negative point. That's why we do max set.
Right. So then it is not sort of monotonic
Yes.
for the negative example.
Yes.
But it is monotonic for the positive.
Yes. So are mostly driven by the positive one. So we most focus on the, so positive constraints are the hard constraint, negative
Right.
constraints are the soft
So,
constraint.
sure.
That because of the max set, those you have to, whatever your monotonicity is saying, it needs that.
Hello world, 42. From here, does it work? Now, volume, where is the volume? Yeah, okay. Is it better like that? Okay. Hello world. I keep saying things. Let's see if it works. Hello. Yeah. Okay. Okay, so I.
This will really
Okay, let's keep it. Let's try this one.
for the
It's perfect.
sorry for this.
No, it's okay. Not your problem. Well, not your responsibility. Well, I know, but yeah, definitely. Yeah, okay. I love your thing. We are hiring. No, we are hiring.
There for 9 years, and 9 years before that he was at MSR, before which he got his PhD with Raja Kuzo. He's done amazing work, lots of papers, lots of amazing tools that are used in industry. And in fact, in 2021, he won the IEEE Cybersecurity Award for practice for the static analyzer Zoncolan.
Zoncolan, yeah.
Yes. And today he's going to talk about measuring data lineage.
Thank you for the introduction, Alicia, and thank you for the invitation. So SAS, SAS, it's a conference that's particularly close to my heart. It's where I published my first academic paper in 2002, been co-chair, already been invited speaker, so many times in program committees. It's essentially my family, my academic family. So let's make this talk interactive. Feel free to interrupt me any moment, ask any question, push back, anything. So I expect some interaction with the audience. This is some work that I did with many colleagues and friends at Meta. So I just get some of them here. So there is Alex, who is a software engineer in security, and Danny is a software engineer in a privacy infrastructure team. Myself, Jason and GCU, they are privacy engineers for tech audit, and Prashant is a data scientist who work very close with. Now, what is data lineage? Have you heard this word before? 1, 2 people, yes, 3. Okay, good. But it's very used in industry. It's essentially the problem to determine how the data flows inside the system, through the system. So why do we need data lineage? Well, because we need to know where the data goes so that we can protect it. Why this is a big problem? Why this is a problem? Why you say, okay, this is just, we know, an instance of information flow, taint analysis, or something like this. Well, the problem comes that in, let's say, real life, the systems and the architecture are very, very complex. They are made of different pieces. They communicate in a very complex way, in a very heterogeneous set of languages and interfaces. So here, oversimplifying a little bit what meta looks like, you know. So we have a front end. Front end are written in different languages. So we have a hack. If you use, let's say, Facebook, you hit a hack front end. You have Python, Instagram, you get Erlang, WhatsApp, you get Java, you get many other languages. Those front end communicates with the web and with the mobile. So for mobile, we have a meta application for iOS, for Android, Reality Labs, etc. So they only exchange information, they send data through. The front end communicates with other things. So for instance, communicates with backend services. Those backend services are written in C++, in Rust, Java, Python, many other languages. Both the front end and the back end, they talk to the offline with tables, for instance, in the offline world, which again have different systems. There's Hive, there's Scuba, there's many others. And of course, there is AI. So we have all the AI models and the way we communicate. And it's not enough. Actually, in this picture, it's not clear, but also service may invoke another service, and when invoking another service, written in different language, for which is harder, for instance, to build a static analyzer. The same in offline, we have pipelines. They talk between them, they talk with AI. So as you see, it's a very complex piece of information. So now, what we want to do, what is data lineage, is essentially the way to capture and compose all the possible data flow that happen in the system. So to understand how the data moves in this complex system, and I repeat, so that we can protect it. Questions so far? Okay, either you sleep or I was very clear. I prefer the second one, or it was very easy, what I said. Now, let's try to be a little bit more precise and give some idea of this. So first one is we want to define what is a flow. So this seems to be a trivial question. Actually, it's important to differentiate between different kind of data flow and execution flow so that we can see how we can combine them into lineage. So, execution flow. So what we call execution flows are essentially when a function calls another function or a service calls another service. Here I use the GenAI for trying to give an idea. So we have a service, we have a second service, there are some wires, there's some information, some data goes through them, but we don't see the information. We just know that this service called this other service. This is information that is collected at runtime. This is, for instance, taking the stack traces, or doing access lineage, or all other ways in which we can monitor something that happens at runtime. Why we care about this information? Well, it's very cheap to compute. It's just taking a snapshot of a stack at a certain point of the execution. It's very precise. You can't argue with it. It happens at runtime. Fine. What is the disadvantage? Well, we don't see which is the data that goes there. And the only thing it says is there is a control flow. I'm waiting for an objection. I say you can also do it at static time. Well, in theory you can, but it does not really work. Doing this kind of control flow analysis at static time to understand how the system call each other just does not work. It's too imprecise because languages, they have craziness as run reflections, virtual calls, pointers, function pointers, and all this craziness. So the only way to get reliable information is doing it at runtime. Then there are data flows. By data flows, we mean essentially when some data, piece of data, set of bits, moves from one place to the other. So essentially, those are copy semantics. Semantics is really easy. Oh, here I try to say some guy is copying a Van Gogh picture. So a semantic is easy because you have these bits that move somewhere, the same bits. Again, this is something that in general you do at runtime because you take snapshot of the heap, you take a certain particular program points, which is the value gets read, when it's written, and then you can do the matching. So the semantics is pretty easy. The disadvantage is that it's not so useful because you miss all the transformation of data. And so if you remember my initial description of of the meta architecture, the data flows through those systems, but also get transformed. And we need to understand how this gets transformed and what happened. Then we have taint data flows. I had already taint, Mayuri is not here, let me see you, in the previous talk. So taint data flow, some way in which you can think about it is actually following the transformation of data. And the data can be transformed in many, many, many ways. So it's very hard. So the semantics of a taint, it's very hard in the real world. So here, my example is more or less, you get some Coca-Cola, you get some wine. Now you put the two into a glass, and the drink you get, what is Coca-Cola, is wine, is both of them, any of them. So how you know? That's the problem with taint analysis. I know the studies about saying, okay, getting the lattice structure, etc., but in practice, it's very hard. So at Meta, we developed several static analyzers to do taint analysis for security that overall capture more than half of all security bugs in all the company. So there's a Zoncolan, it's inspired. It's Forac, the name comes from a mountain in Italy, very hard mountain for climbing with a bike. Most of you, I think, they know that I'm a little bit into cycling, just a little bit. Then we have Mariana Trench, Pisa. So if you want, you can go and try Mariana Trench and Pisa. They are open source. And now, what are the advantages? Well, the advantage is that now we capture what we care about, which is the transformed data. Questions so far? Yes.
What do you mean by data here? First of all, is it like per user that is being tracked, or is it like just sort of data from Instagram flowing into Llama, or what granularity do you need to track?
So the question was, what do we mean by data? Data is essentially in a way, it's a generic concept if you want. There is some way which we have in data lineage to annotate what is the data you care about. It can be a field, it can be a column in a table, it can be all the table, it can be some input coming from some particular endpoint or I think. So it's pretty generic. Let's say that also our tools allow you to specify them in a very generic way. And the same for the sinks. There can be many different things. Can be a table, can be a column, can be a logger, can be many things. So the system is generic in a way, so that we can capture the one that are relevant. Yes?
What if it is bad to flow some data as it is to a certain place, but it is fine to have that transform form to flow into that position? For example, maybe we don't want other people to see who are my follower or who am I following, but I'm happy to let them see the count of my follower or the people who are following.
Yes. So in this case, we have two things. We have the tooling data lineage, which is the one that builds the graph. And he has this huge graph for all the data goes. And the graph, in a way, is agnostic of how you use it. So you get the information you need. Then on the top of the graph, you query the graph for the information you need if you have a violation or if it is correct. So it comes afterwards, which actually, by the way, is the way we also do taint analysis. The analysis, they are not opinionated on what is taint. They are not opinionated if this one is Coca-Cola or wine or any of the two. Just say, hey, there is some drink which comes from Coca-Cola and from wine. Are you happy with that? You are not happy with that? Something like this. But this is in the second step. And then there are what we call indirect data flows. The best thing I could think about is that there is this kid with tainted hands. Then there are cars going through, and then it may touch or not the cars, and then essentially taints the cars. This is static time concept. Now, it's interesting from a theoretical point of view. It allows to find some information that goes from the control into the data. But in practice, we found that it's not so useful. It's very easy, very quickly, just taints all your code base. Everything depends on some loop on this thing. So we don't really do this, except in some particular use cases. I expect pushback here. No one is doing pushback. Okay. Oh, so okay. So the question is that the cryptographer. I guess it goes to the previous question. So there are two things. There's discovering the data, and then there is the policy. We call it the policy, the attacker model. Now, we can argue about cryptographer and use cases, but our experience is there are only limited cases when this is useful. And in this particular case, essentially, you can override having the generic framework and focus on this particular use cases. So.
Regarding these branches, I guess one place there might be a lot of branches in the code base is when people are running these A/B experiments, right? Like some users are getting this new feature and others are not. So, and then in fact, I presume that when you're running the experiment, you want to make sure that when you finally switch, you adhere to some privacy policy. So is that something that the tool sort of makes a special case for?
In the particular case, no, because yes, I think it makes sense. So the fact is that it's not the A/B testing that is tainting your data. It's really how you're using the data in the branches, and we track it. So I guess you want to know more about data lineage, how we combine these things, but I'm not going to talk about it today. It's a talk by itself. It's a pretty complex technical problem. How you scale up, for instance, it's a huge database. How you make sure that it's stable. How you make sure that when you combine static and runtime information, you get things that matches, because now you get the inputs from different tools that even if I'm talking about the same thing, they're talking with two different output formats. So now you have to match all these things. Pretty complex one, not going to talk about it, sorry about that. You have to invite me again. Just kidding. So what I was trying to explain is that each tool captures different kinds of aspects or properties of the system. When we put them together, we get this big fruit salad. And now we want to understand about this system, for which it's hard to get a quantitative explanation, but we can opt to get a qualitative action. We get a qualitative explanation. And in particular, the important thing is that each tool, which is runtime, static analysis, et cetera, they make different kind of assumptions. And we combine together, but things can happen. Now, the way where we solve the problem essentially is taking a step back and talk about all data lineage as a system that we want to evaluate qualitatively. This will provide us a global understanding of how the system works, and also to have something very important. Now we can put numbers to the trade-off that, for instance, we did in our static analysis and make choices. Also, this enables to set goals to the team or different teams. Say, hey, we want precision to go up from this N%, or recall to go up from this K%. Or how do we balance those two things? Now, what should we measure? I guess it's easy for this community to say, okay, we need to measure precision of recall. So precision is what is the ratio of false positive, and recall is what is the ratio of false negatives. We may measure, and actually we do, other things as reliability, storage space, the cost of computing all of that, et cetera, et cetera. So for instance, we don't do taint analysis at runtime because it's just overkilling. So that's, and I'll give you the time to read this slide. Are we good? So we know how to build a static analysis which are sound from CC77. So thanks, Patrick and Radia. In practice, what happens is a static analysis, they make assumptions. They just consider a subset of the possible execution, and then they are sound with respect. You build a sound with respect to this assumption. Commonly, things that static analysis do, they say, oh, reflection, it's okay. We are just assuming there is no reflection. Or if you do JavaScript, it's eval. All the program analysis that I know that are modular, they assume that the parameter don't alias. All of them, no exception. Exception flows, they are always ignored. They never say, hey, the data goes there, then we throw an exception and we go there. There are assumptions when they have a calls to external libraries, let's say GNI, or use unsafe code, even Rust is unsafe code. The execution context also matters. You don't think that you are in the data center, then, I don't know, the CPU gets a cosmic ray and then flip the bit. Async routines are usually handled as function calls, but they are more complex than that. Some analyzers, they do integer overflows, not others. And also compilation works, there are no bugs in the CPU, in the VM, et cetera, et cetera. Runtime analysis is this thing too. It's a long set of assumptions are made, a lot of trade-off for granularity, performance, sampling, et cetera, et cetera. And now when we do the data lineage, we combine those things. Please interrupt me and push back. I'm waiting for people. Way of putting this with Venn diagrams is that among all the possible flows you can think we can have in all the infrastructure, we are interested only in the one that corresponds to code that is really written in the code base. And we do an over approximation, so like this. In practice, this is what we got. So what we discovered by lineage as false positives. Some of the false positives are completely out of what is the possible flows. Some are the possible flows, so those are, say, benign, not the one interesting. And then we get false negatives, where things that we like to discover, but we don't. Okay. Something we know also is that we can increase recall while reducing precision. So all the assumptions I said before, well, we can remove them. So let's say for reflection, I can easily say, okay, now every time I have a reflective call, I can just assume I can call any function, maybe any function that maps the signature of the types of the particular function. That's one way. Exception is the same. We go and we can instrument every line, every point in the IL where an exception can be thrown, and then we make this complex control flow graph, and yeah, we essentially increase the recall for that, and so on and so forth. We can fix them in a way. But now the question is, we are improving recall, but now we are also reducing precision because we're introducing many false positives. How we quantify that? How we know what is the correct trade-off? Remember, we have this giant graph with big graph, only a little percentage. Increasing precision is a lot of work or a lot of wasted time, if you want. So we use it, essentially, we use quantitative methods, we use the measurements I'm going to talk about to try to understand what is the impact of improving, let's say, static analyzer, improving the recall with respect to the precision loss that we get. So I'm just making an example. Assume that we know for certain reason that the recall is 90%, precision 80%. Assume that we discover, hey, this comes because of this some reflective call. The analyzer ignores this call. We don't know there is this particular flaw, so we miss a flaw. Okay, let's do the worst case for reflection. Well, now we measure, we can see, okay, recall went up, great, but then precision tanked. Now the question we can ask is, okay, is it worth it? Maybe it is, maybe not. Maybe the way in which we fix the recall is wrong, or it's too expensive. We need to find another way for doing it, which actually happens in practice. We have frameworks which are, at their heart, they use a lot of reflective or dynamic features. And the way we handle them is not by giving the semantics of this reflective feature, but looking at higher level, saying, okay, now you are using this framework, and we know that it is this behavior. So let's use this behavior instead. So it's not solving the general problem for recall, but it works very well for this particular framework. So this is the cases where we essentially push the recall up while precision stays more or less the same. Questions? You like that? So I expect a no, I expect questions. I expect pushback. No pushback. Too easy. So how do we measure? Well, we use data science, we use sampling. It's not effective. There's no way we can go and see all the results and say false positive, not false positives, true positive. And well, we need to sample. Sampling in general can be expensive or cheap, depending what you're trying to look at. For instance, when you look at false positive, sampling is super cheap because you have all your results, you have a random number generator or something like this, it picks some of these results. You need to get some that are statistically significant. I'll talk about it later. And then you give this to human beings, engineers. And now those engineers should say, is it true positive or is it false positive? This is expensive. Even if they are very skilled engineers, it's still human work, takes time. And in general, evaluating them, it's non-trivial. Understand if something is a true positive or false positive. True positive in general is pretty easy. False positive, it takes some time because things happen. So there is a cost in evaluating them. False negative goes the other way around. Sampling, again, is expensive because now we need someone to provide the ground truth. So we need the human beings. We can't get this data from other tools because otherwise our testing set will be biased by those tools. So we need human beings that provide this ground truth. And then evaluation is super cheap because once you say, okay, I see that the data flows from A to B, a human being provide it, then we look in our lineage graph and we see if there is a data that goes from A to B. If there is, and then there are technical things, we can talk about it, is that maybe find it, but for the wrong reason. So you need to put some control in between to make sure that really the data flows where you want it to flow. But in general, this evaluation is very cheap because machines do it. So next two things we care is how we make sure we have enough samples to get significant results from a mathematical point of view, and two, what are admissible traces, things that we care about. I start from false positive because it's the easy one. I don't know, I'm making good time. I think I have a lot of time. Yeah, half an hour. So I have a lot of time. You can interrupt me. It's yes.
I'm curious. So I thought the risk of having high false negative. So we don't want to have high false negative when the consequence of missing a problem is very high. But this is not covered in the previous slide. So I'm curious whether I'm misunderstanding something or.
No, you're right. And the missing slide were just numbers I made up. So those are just examples. Yeah, so we need to have the recall very high. So those numbers were just made up for the purpose of illustration. Also, the next one, all the numbers you see they're all made up. But yeah, and this is actually the great thing about it, because now you can quantify those essentially the recall. And actually, there is an interesting point too. You may have if precision is low and recall is very high, maybe the case that in practice the recall is also low, because now you are going to overflow the user with many, many, many results. And they can't make the decision anymore. We are human beings. No, there is a certain attention span. So this is also why it is important. But it's non-technical, if you want. So it's not the subject of this talk. Now, false positives. Well, I said before, we can't triage all the results. Even if we take a subset for a particular problem, we are considering there are just too many results. looking at all of them is just too expensive. So here we're not talking about 100 results. We are talking about thousands of results. I think they should be seen it. So instead of saying, okay, what is the false positive proportion, which is what I always see in papers, and I'm also guilty for it. In the papers I wrote in the past, there's the proportion. What we care is a confidence interval. We essentially want to say that our false positive with a confidence X, C, no, X, I used the X on the slide, with a confidence X, it's in this interval. That's what we care. We want to get an estimate for the upper bound, lower bound with a given confidence. This is different from saying my false positive is X%. Now, the algorithm is pretty trivial if you want, high level. Essentially, we randomly sample and traces. We give to humans, say, okay, true positive, false positive, please mark them. We have automation to help making this very quick, record the results. We compute the proportion, and then we use some math. Can you guess what we use? Well, in general, we use normal distribution, no? That's what we learn at school, because essentially evaluating every value, as we sample, evaluating every result to be a true positive or false positive, it's essentially is having a binomial distribution. We know that if we run enough of them, then because of the central theorem, central limit theorem, then it will have the shape of a normal distribution. And also we know nice things that if we had almost twice the standard variation, we have 95% of the results. So actually it's 196. In the late 20s, mathematicians, they started also interested in say, okay, what is the confidence interval when we get this data? So there is some nice math that says, okay, when you assume a normal distribution, this is the interval, the confidence interval. Essentially, you take the precision you observe, the ratio you observe, then you have this thing is called the z-score. I will talk about this, about what the z-score is. Not what it is, but in other formulas, why it is important, which is essentially this interval, if you want, this point here. It's 196, and then it's the standard deviation of the population divided by the number of samples, and you take the square root. Some math, you need to believe me, and I believe data scientists. No, I read it too. You can develop it, it's just standard math. Cool. So we are an algorithm. Yes?
Maybe this is showing my ignorance about some statistics, but I presume these flows are not sort of independent, right? There's this giant program, and flows are related in a very deterministic way. Does that mess with some of these assumptions of the sampling, that you can just do n random samples and still work? It still works.
So first disclaimer, not a data scientist. So we trust data scientists. I think for the purpose of this evaluation, you can assume as all to being independent. So because we don't know information. We hope that if we get enough information, then we can revisit the model and then refine it. So my understanding in statistics, again, not a data scientist, is that you first kind of try to start from the worst case approximation. You get some data. From this data, now you refine your model. You keep refining. So that's, I guess, how polls for election work, et cetera, et cetera. So this is the simple one in which essentially we have no idea about the precision of the system. What's the problem? But actually, normal distribution is not good. So I just, brought you to the error. I make you believe something which is not good. Why is not good? There are essentially two problems. Now, here are numbers made up. Suppose that we want to have a confidence of 95%. Seems good, no? 95%. Usually in statistics, a 95% confidence interval with error of 5%. That's made up. Now, assume that now I have my data and I get 10 samples. All the 10 are true positive. So my proportion is 100%. And well, if I apply the formula before, I get that my interval is between 100 and 100. Perfect. Now I double the number of samples. and I get the same number of true positives. My interval is still 100%, 100%. And I keep doing this, 30, 30, 100%, 100%. Now, intuitively, does it seem correct to you? Imagine here I have 2,000 samples. I will get 100, 100. Why should I get the same result if I have only 10 samples? Intuitively, if I tried something 1,000 times and always succeed, I have more information, I have more confidence than if I tried it 10 times or one time when I succeeded. This seems wrong. Second thing, which is actually very fun to me. Assume that now our proportion is 0.9, 90%. What it means? If I run 10 times my experiment, 9 times I have a true positive. 20, 18, 30, 27, etc., etc. So you would say, okay, my precision then is 90%. But we say we don't talk about the ratio, we talk about the interval. And the interval, if I use the formula I showed you before, it's really fun. Because when I have 10 samples, it tells me that my interval for precision is between 71% and 108. How can it be 108? And if you increase the number of samples, well, it goes down, but it's still over 100. 76, 103, 79, 100.7, and then eventually when I get to 100, now I have 95. So the interval is shrinking. So in a way, it's getting better, but this number is bad. So essentially there are two problems with the normal distribution. The first one is the normal distribution does not work well when you have few samples. Remember, evaluating false positives is expensive, so we can't opt to get a large number. So, but still you want to get a few few samples, and still derive some result which is statistically significant. So instead of using the normal distribution, we use something which is called the t-distribution or student distribution. Who knows about it? Cool, yes. I didn't know. So I learned this from data scientists, but I found it super cool. And for those who don't know, so the interesting part of the t-distribution is that close to the extreme, it's wider if you want, it's fatter. So it means that when our precision goes close to the extreme of not 0%, but more towards a 90%, now we need to use this one because it gives a larger area. The second problem is for the formula to compute the confidence interval, the one I showed you before. It's too approximate. So there's a paper of 1927 or 29, something like this, from a English mathematician, Wilson, that he came out with this formula, which I don't pretend to understand, which is called the Wilson score interval, that gives a better estimate of the confidence interval. So something to note is that the t-distribution, when we increase n, so get more and more samples, becomes the Gaussian distribution. Who knows about the Wilson interval? It's super cool. And it's the one you want to use if you have confidence intervals. It works very well also for small n's and at the extreme. Now, let's take the same number set before, and let's apply what I just told you. Now, if you use this math, you say that when you have 10 samples, the confidence interval is between 72% and 100. So maybe we have no false positives, so it's 100. But we have only 10 samples. So, hey, 72%. If we increase the number of samples, then our lower bound goes to 83, with 30 goes to 88. So the more sample, the more run experiment, the more sample we have, if we get to the same proportion, our interval gets better, better, and better. And this is with a 95% confidence. We can change this number, get 99, etc. By the way, there are websites where you can try those numbers. It's pretty fun. So this is just ones I get from Google. So first problem is solved. Second problem, the one that we get these very large intervals which are over 100. Well, you see how now we get a number which is more reasonable, because if we get 9 samples that succeed out of 10, with a pretty wide interval. We can't say that is a 90% precision. It can go as low as 59%. I have to admit I was shocked when I discovered that, because that was not my mental model. Also because if you see, it's not centered on the proportion. It's not 90%. So our interval essentially it's moving a little bit, if you want. It's unbalanced. But intuitively makes sense, no? You did a few samples, you did a few experiments, and you can't claim that your precision is 90%. Maybe it's better, it's 98%. There's a little chance that it's better than 98% because you have at least one case where you miss, so it can't be 100. But with 95% of chances, you can say, okay, it's more equal than 98.2 and larger than 59. But also, you know, your precision will really, really be bad because maybe the samples you took, they are too small, too, I guess in a way also answer your question, too biased, and then it can be bad. And well, if you increment the number of samples, always the same ratio, your interval gets better and better and better. So, and the interesting stuff is that this is decreasing, because if you run 100 times, you get 90, so it means that you have 10 failures. So your chance of being close to 99 is going down, 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 and down the more you run. Questions on that? Yes.
Have you tried using the beta distribution and Bayesian statistic method to get a credible interval?
The TLDR is no, we didn't. So I think we should take it offline because the reason is complex. Yeah. Sorry about this very short answer and unsatisfactory. So. False negatives. Now, the problem with false negatives is that actually we don't know. We don't know if we are missing something. So what we do? Well, we use a technique which are pretty common in a machine learning, is that we build a ground truth set. Essentially, we get some humans to provide some flaws that are important, that we want our tools to find it. And then starting from that, we test our tools if they can find those flaws which are pertinent or relevant for humans. It's very important that those tools that are not produced by other tools, because otherwise we get some biased information. We're only saying if one tool can find something that is found by some other tool, which is, it has some interest, no? You want to prove that one tool is better than the other. So how you do it? You take some data provided by this tool, and then you see if the new tool finds it. And then you can also, if it matches it, you can do nice math to also say, okay, how confident you are that it's really better than the other one. But this is not what we are discussing here. So we need these flows to be manually correct. This is expensive. Again, it's in a way even more expensive than finding true positive or false positive. And also, not all the flows are important. No? And the one that we really care is essentially the one that we know our tuning, our lineage, static analysis, if you want, in general, they should find. Now, I summarized the interesting flaws, the admission flaws in the ground truth to satisfy two properties. One should be representative, and the other one should be relevant. What representative means is that those should be common paths that we expect to see in the code base. Now, imagine it's JavaScript. In JavaScript, I can have eval. Inside eval, I have another eval, and then inside this eval, another eval. Totally admissible program with the semantics, et cetera, et cetera. Is this representative of the code that we write? Probably not. I don't expect a professional software engineer to write eval inside eval inside eval. So adding this kind of flaws to the ground truth, it's not really interesting for measuring it. Measuring the recall and the precision of the tool. Also, let's say about frameworks. We know that in our code base, there are some approved frameworks and others that are not approved. So putting some ground truth, which uses these frameworks that we don't have in our code base, well, it's not useful because we know it's not in the code base. So we expect it not to find it because they are not there. So this is one thing. And then they are relevant. So they are things that we really care, things that we want to find. So for instance, if there are some flaws in debugging code, well, we really don't care about them. That's not things. Or testing. Testing also, it's not something. Honestly, it's more for a functionality, but it's not something we expect the tool to find. And we have some other criteria to make sure those are really what we need. But this is helpful because this can guide the humans on which flows to prepare. We have all a system to approve those flows, et cetera, to make sure that it's a consistent set of ground truth with matches those two criteria. I think I forgot a third one here, which I told verbally. I just realized now is that they should not be provided by other tools. We don't want them to be biased by some other tool. Because collecting ground truth is expensive, we want to get some idea of how many ground truth traces do we need? How many we can ask humans to collect? Idea we say, oh, collect 1 million, 1 billion, not feasible. But what is the number, minimum number if you want, which is interesting enough so that we can derive some statistically significant results? This is actually a format that I understand too, and you can derive from previous formulas on a confidence interval. Essentially, you can compute the number of samples if you know the z-score of what is your level of confidence. So if you want 95%, your z-score will be 1.96. They are calculated online to find it, or there are also tables in the old times. This is a little bit harder. It's the z-score of the desired power. I have problems to explain easily. With the math, it's actually easier. But the idea is essentially you are pumping up some values, you're bringing things up so to improve, your results. Then this is the proportion that you get, and this is your margin of error. You want an error of 5%, 10%, 20%, 50%. I plotted several cases to see which is, what are the number of samples you require. So if you want to have a confidence of 80% with a margin error of 10%, at the worst, you need 113 samples. When is the worst case? The worst case is when your proportion is 50%. You don't know, and this is what you do essentially. You assume the worst case. The worst case is that my recall is 50%. How to prove it? How many samples do I need? 113. It's interesting that if you want to prove that your recall is very bad or very good, you need way many lower, smaller set of examples. Now, assume that I want to increase my confidence level with the same error. Well, now I go to 150. If I want to keep the confidence level to 80% but reduce the margin of error, now I go 450. So this is pretty interesting, isn't it? If you think you have two variables where you can move. You can move in the confidence interval, or in your confidence. And if you want to increase your margin of error, the number of samples required just goes very high. You can play. There are calculators online to get those numbers. And if I want my confidence to be 90% and the interval is smaller, now I go to 600. So it grows very, very quickly. Questions? Clear so far? Are you fine with what I'm saying? No? So how we do it in practice? In practice, essentially, we consider the worst case. The worst case is when our ratio is 50%. So when our ratio is 50% here, it means that we need to collect 113 samples. That's and to get a confidence 80%, with a margin of error of 10%, so it's pretty wide. This is also for only for illustration purposes. They are not real numbers. I just made up the numbers for explanation. So it's easy. Get 113. We run the math. We ask to provide 113 samples. What we can derive with? What we can say now about the recall? Assume that we run our experiment and we get a proportion. So we see that out of these 113 traces we have we want to find, we only find a portion of it. Let's say we find 90% of them. What we can say now? What about the recall? Talking mathematically. Well, assume that we wanted to prove our assumption would be that recall is 90%. If this was the case, then we needed 40 samples. So we have way more samples of what we needed in order to prove the thing. What it means? Well, just get a table over there, is that essentially we can interpret the data in different ways. This is what it means. So let's see how to explain that. One way to say this is that, okay, I can keep the confidence to be 80%. We needed, for having 80%, the number of samples to be 40, but it's 113. So now I can have a very narrow interval. I know that with 80% confidence, my recall is between 86% and 93.2%. So this is one thing I can say. So I just get not great confidence, or I don't know if it is great, 80%, but a narrow interval. Or I can say, okay, maybe I can increase my confidence to be 90%. In this case, I would need 55 samples, which means that my interval now gets wider. So now my interval of confidence is wider, but my confidence, the value in this interval is higher. And the same if I go 95, now we need more samples, and well, my interval is even wider, so it's 11%. Cool. And I'm done. So what are the conclusion of this talk is that the assumption we make in our tools, they can be empirically quantified. Essentially, we need a kind of external and quantitative verification of the assumption we made in our tool. This allows us to reason quantitatively about the different choices that we make when we build our tools. What I say here actually has almost nothing to do, or nothing, it has all to do, but is not related only to data lineage. You can apply this to any static analysis too, because essentially you are taking the static analysis as a black box. You can ask questions about, okay, I want to increase precision, what I lose for recall. So many tools, they do a lot of those assumptions, say, hey, I want to have very high true positive ratio, but then they are tanking the recall. It's, yeah, we see about CodeQL earlier today, other things. So are you ready to take this or not? Then you can start putting, a cost on the time to triage the false positive versus the recall. So you can start reasoning quantitative on all these things. Now, it's important to use statistics. This is really the important thing. So that's why, for instance, we get close to data scientists that help to make sound statistics. Giving a number, it's not the right thing to do, a single number. What we really want to do is to give a confidence interval. What is your confidence that the value lies in that interval? This is the way to reason about it. And I'm done.
Any questions?
Maybe. No, it's an easy one. When you got older, your questions are easier, you see. Yeah, okay. because you combine many tools, the information you get is on the whole stuff of the tool, but it might be maybe more interesting to have the influence of each tool in the lack of precision.
And also a very hard one. Actually, what we say here, you can apply also to a smaller granularity. And actually, we do it. For the particular static analyzer, we do exactly that. We have all the data lineage where you compose everything together, and then we can focus on certain particular pieces of the data lineage which we care. So for instance, the static analysis zone column gives us information for the code base so that we can essentially know, okay, in a way you can't do better than this tool. If the tool has a very low precision, you can't hope that all the data, I kind of contradicting myself, because you can use runtime analysis to improve the precision when you combine. But you can get a neat recall because runtime analysis will remove some flaws which simply were not observed, but they are feasible. It's really a balanced game. Yes, yes. So the question is, one tool can be more precise and the other one is less precise, and then there should be some equilibrium. Yes. This is actually also a way in which we drive the choices that we do for the analyzer. So if we want to, let's say, change the widening, let's see what it happens. Or let's say, let's get a different abstract domain. Let's see what it happens. So we can start getting numbers on what it happens. Now, we can also say what is the impact on one tool for the other. So let's make the simple case. You have static analysis, there are virtual calls. Those virtual calls, the static analyzer does not know to what they resolve because they are virtual. It's a runtime concept. So it says all of them. That's what zone column does. You can call it all of them. Now they can fan out a lot. So decrease precision by a lot. You can say, okay, what I can do is I use runtime logs profilers to see at this particular point in the program which function I observe, let's say 1 day, 2 days, 1 week, and then instruct zone column only consider the one that we saw at runtime. So this clearly may miss some flow because if we haven't seen them at runtime because it's something that runs, I don't know, once every month, and our window is 1 week, we miss it, so we missed one flow. But also increase precision by a lot. You know, now we can use a very precise analyzer information to increase the precision of another one, but it will reduce the recall of this other one because the runtime analysis is sampled or there are windows. So does it answer your question? Okay.
On your title, because you say data science and there is no neural network, so it's it's not really data science.
Oh, do you know the joke? What is a data scientist? What is a data scientist? A data scientist is how they call a statistician in Redmond and Silicon Valley. That's only statistics. We don't have AI. Well, we have abstract interpretation, so we have data AI.
So maybe you could share, either some data or maybe some anecdotal stories about the impact of this to both the tool developers and as well as the users.
So anecdotes. It took some time to get this mind shift to go quantitative, no? Also to me, to be honest, I guess it was always, okay, there is this flow, we're missing this flow, let's fix the analyzer so that, we can see this flow. And then we run a couple of tests, and then we say, hey, it's okay, not so many results. Starting thinking about confidence intervals, it takes a little bit of more effort. Because now, let's see, you see numbers like that. You run, you just sampled 30 example, true positive, I expect, okay, it's 100%. But actually, it says, no, I can go as low as 88%. And maybe I'm unhappy with 88%. So there is this thing about, this mind shift also as the tool developer. On the other hand, it's easier to communicate with leadership because the mental model here is, okay, give me a number, give me a goal, how we can essentially improve this thing. So what's essentially how to measure those things. And traditionally is not something we have in program analysis. We don't have the mindset of measuring those things. No. And this was a kind of, let's say, I don't know, disconnection is not the right English word. There was some communication problem, so how to get it. Now, getting something quantitative helps a lot. In practice, what it means is that when we set goals, we can set goals based on numbers. We can say, okay, this particular thing or this particular tool, for instance, that contributes to this, we want to increase the precision, we want to increase the recall. So it's interesting.
Yeah, so I know you were mentioning the drawbacks of the uniform normal distribution, and that's solved by the T distribution. Instead of T distribution, can we use other distributions like, say, the F distribution? Would that work?
I'm going to give you an answer you don't like. I don't know. Or actually, top, because we are doing absent interpretation. Honestly, I don't know. That's why we pair with data scientists. So that's this is my intuitive understanding of the math. I've been reading a little bit, but probably there are better ways to improve it. But that seems to work pretty well in practice. So I don't know. I can ask the question actually offline and I'll come to you. Yes, okay.
Yeah, let's thank the speaker again. Okay, so our next talk will be by Kate Lamb, who's going to be telling us about lift offline instruction lifter generators.
Okay. Good afternoon, everyone. It's my great pleasure to be here to present to you our work, Lift Offline, Instruction Lifter Generators. This is joint work by Nicholas Coughlin, Alistair Michael, and myself, Kate Lamb. We are all employed by the Defence and Science Technology Group of Australia, and our research group is located at the University of Queensland. Briefly, this work concerns applying offline partial evaluation and static analysis techniques to generate an instruction lifter for a particular instruction set ahead of time. Cool. Okay, so in order to reason about assembly code, you require accurate, trustworthy models of the instruction set architecture. And in particular, you need to know about the behavior of instruction opcodes. Conventionally, this is provided as some multi-thousand page document, which takes minutes to download and is still not extremely precise. As a result, existing decompilers derive from this handwritten semantics with limited correctness arguments, often because they have to fill in gaps in the English prose documentation, which is not well specified. But recently, ARM has published this machine-readable specification in its architecture specification language. And this is kind of a formalization of the pseudocode, which you would find in these reference manuals. And it's machine-readable, it has a grammar which can be parsed, and it's structured with this decode tree going all the way down to particular instruction encodings and their semantics. However, these formal models are still difficult to integrate with tools using them, and this is for a particular reason. Alistair Reed, the person who was responsible for primarily pushing this work at ARM and now Intel, talks about this gap between different consumers of the architecture model and the different interests they have. The architecture model is obviously made by ARM. They have one set of interests, which is to verify their own hardware. And for that, they need pretty intricate details of all of its behaviors. Where we sit, we are interested in using the models to analyze software systems. So that's obviously much higher level, and we can abstract away some of the lower details. So we need a tool to kind of flatten out the specification, distill it into its essence, and hide some of those lower level details. This is something we have done in our previous work. In a paper called Liftoff, published at FMCAD last year, we provided a tool called ASLP, which is an online partial evaluator for ASL. It works something like this in this highly simplified example. Given a specification and a known opcode, it applies online partial evaluation, essentially taking the opcode as concrete and applying techniques such as constant propagation as much as possible to reduce it to a much simpler form, as you see on the right. This was validated by randomized differential testing against an interpreter for the ASL, which just used the original full specification. And this found some bugs in the instruction semantics of existing decompilers, which points to the usefulness of this approach. However, when it comes to integrating the ASLP work into downstream tools, we found there were some problems. Fundamentally, online partial evaluation requires traversing the specification in its entirety for each opcode. And this has obvious disadvantages. There's this tight coupling between consumers who want to use ASLP and the OCaml runtime, which ASLP is written in, as well as the entire specification itself. It's difficult to reason universally about the produced semantics, since it only handles one opcode at a time. Kind of the best thing you can do there is just exhaustive testing, which is not super satisfying. And also, because of this difference between ASLP being written in OCaml and other languages being written in C++ or whatever else, there's this need to transfer between the intermediate representations, which is another source of error and inconvenience. Okay. So our aim in this current work is to generate a standalone lifter in the style of handwritten lifters such as those which already exist. And here, a lifter is a program which returns the instruction semantics given a particular opcode. Crucially, this does not make up a full decompiler because it needs to be composed with components such as a disassembler to partition the binary and a control flow reconstruction as well. But it's a fundamental part. Okay, so the observation we make is that the ASL specification itself, which you'll see on the next slide, is structurally similar to a handwritten lifter. However, it differs in a key way. And that way is a traditional lifter distinguishes two stages of operation. It has the lift time, where the lifter itself executes. This is typically written in C++ or something else. And then it has the runtime, which is, we say execution, but really the interpretation of the semantics produced by the lifter. And in runtime, we have things such as register accesses and memory loads. But the observation we make in this work is that although ASL does not differentiate the two, we can deduce it through this process of offline partial evaluation. Okay, so now an example. This is a highly simplified example of the machine readable architecture you might see for the add instruction, which adds to registers xn and xm and stores them in xd. You can see it within the specification, it just directly reads these and then directly writes it. It looks a bit like an interpreter almost. If we compare this to a decompiler such as retstack, you can see it performs in this function called translate add. It fundamentally uses the LLVM IR builder to create an add operation. And then it creates a store operation and a load operation as well. And this is the separation of stages which we were talking about. Okay. So the offline approach to partial evaluation is to generate a lifter ahead of time in two main phases. The first phase is a binding time analysis, which is something like a taint analysis, where we mark static values such as the opcode itself and some constants as lift time. This gets propagated into expressions and following statements, and computations are marked as lift time if all of their inputs are lift time, otherwise they're marked as runtime, as you might expect. This is followed by a transformation, which uses the result of the previous operation. For lift time operations, we make no change, and for runtime operations, we translate them to a function call, which defers their effects by constructing something like an AST. And we'll see an example of this in the next slide. Cool. So abstractly, this difference between the online process and the offline process at a super high level is somewhat akin to currying. In online, you need both the specification and the opcode to produce the semantics. Whereas in the offline process, you take the specification and then you get this separate object, which is a lifter, which takes only an opcode. Okay, so here we bring back the online partial evaluation diagram just as a reference. The online process goes down towards the bottom, and it will generate a lifter. So using what we said on the previous slide, it sees that the if statement's condition is entirely lift time because it depends only on the opcode encoding. So that will get emitted straightforwardly. However, the branches are runtime because they depend on registers. So they get emitted as these gen functions in, again, a simplified format. So instead of performing the loads and stores immediately, we defer it through these helper functions, which may construct LLVM IR or something similar. And the same happens for the false branch, as you might expect, the difference being it generates an add versus a subtract. And then, upon executing this generated lifter, one expects that we should arrive at the same results as the original online partial evaluator. This is the correctness criterion, which we will aim to test in our validation methods. Basically, that this diagram commutes, and additionally, it's equivalent to the original specification which we started with for all opcodes. However, with this offline generated lifter in hand, we can in fact do more with it. So you'll have to bear with me as I cut a diagram across slides. Blink. Okay, so this being from the previous slide, we can take the generated lifter, and because this is a program which has an AST, it exists, we can manipulate it in ways such as translating it to other languages. For example, we can translate it to C++, Through a simple syntactic translation, the if statements look slightly different, and we call out to some abstraction somewhat matching LLVM's IR builder, just because it's convenient. And then, if we evaluate this given the same opcode encoding and an IR builder which constructs LLVM, you can just as easily obtain LLVM semantics for the same opcode. Just like that. And to compare this to what you had to do with the old lifter, you would take that line and then manually translate it to LLVM, which is a rather unsatisfying experience of AST shuffling. Okay, so to clarify this difference here, we have the different operations in this table and the lift time and runtime variance. This should be pretty obvious. The only interesting thing is the branch, which we implement in runtime by deferring it to this gen branch operation, which has an associated switch context method, which takes one of these TFJ, representing the true, false, or join of the conditional branch, and kind of switches the active location, active basic block, you can think of it. Okay. But yeah, so the interesting thing here is translating to different lift time languages for the lifter is merely a syntactic translation. And also, one lifter can target different runtime languages, such as by polymorphism or runtime duck typing. It just has to provide the interface signature matching that IRB we saw on the previous slide. So this is pretty good. But there's still some work to do. So in the original work, online partial evaluation is extremely powerful due to precise knowledge of the opcode. And this is fundamentally the defining difference between online and offline partial evaluation. So in the previous approach, post-processing could clean up many suboptimal structures, which we can't do this here because it doesn't know concretely what the opcode is. But we can make it, we can tell it. And the trick, okay, sorry, wrong slide. But yeah, so the offline residuals are less amenable to post-processing because they have this over-approximation, and simplifications based on algebraic rules are less effective. And this is a common idiom in the specification where, based on checking bits in the opcode, a register operand is either an actual register or a virtual zero register. And this gets transformed via the offline transform into something big, but you'll notice that it always has the gen add at the bottom, even when it may have been simplified in the case where temp equals 0. So yeah, so we have this suboptimal residual in the case where the encoding bits are not equal. And we want to improve this. So we note that the defining difference between online and offline partial evaluation is knowledge of the precise value of the opcode. So we can actually do a trick to encode this within the analysis domain. What this looks like is lifting our previous abstract analysis, abstract interpretation domain, into an opcode sensitive analysis. So given an abstract domain A and less than and a transfer function, we derive one operating over a domain of functions of opcode to A, where the comparison operator is translated pointwise, and the transfer function is this funny thing which is a function because it is a function in the domain, but it performs a substitution of the opcode in place of the unknown encoding variable and then passes it to the original transfer function. Okay. And in order to implement this efficiently, we make the observation that these objects of opcode to some A are efficiently represented as multi-terminal binary decision diagrams, which we'll see on the next slide. Cool. So this is the same zero register example as before, and here is an empty BDD, which represents the opcode sensitive analysis for this block of code. So here, as said, it represents functions of opcode to A, where here A is a flat lattice of all of the constants. And bits of the encoding opcode are decision nodes, and values of A's are terminal nodes. And crucially, to make this fast, we use a fixed ordering of decision nodes from most significant to least significant bits. And this is based on the observation that the architecture is structured such that the bits towards the left of the opcode are more impactful, making bigger changes on the behavior than the bits towards the right, which typically only affect registers and immediate values, and so on. So, with the result of the multi-terminal binary decision diagram, we use this to transform the lifter to produce more concise semantics. This is done, as you might expect, for conditionally applicable simplifications. We split the statements by inserting a branch into applicable and non-applicable cases, which allows you to apply the simplification where possible. This is done for dead code elimination, copy propagation, and constant propagation. And just to tie it back, the previous slide's example would become something like this, where we assign to x2 the addition under the particular condition where it needs to be done, otherwise just x1. So it makes it a bit that much simpler. Cool. And for evaluation. So as you might expect, the offline generated lifters are much faster at lift time, at the obvious expense of compilation time. This is on the table to your left, with the original online lifter taking 2 seconds to compile, but all of the other lifters, which we also translate to languages Scala and C++, take substantially longer to compile. And this table is actually excluding the 10 seconds which it takes to do the offline partial evaluation process. And these times were not without work either, so it took work to get it down to these numbers. In the Scala lifter, we had problems with the JVM having a limit on the size of its emitted bytecode in each method. And for C++, we had problems with template instantiations. But yes, on the right-hand side, you can see that this is much faster at compile time, at lift time, sorry. For the instructions tested, it's about a 100 times speedup, which is pretty good. And certainly useful if you're using this tool in a setting where you expect to encounter many opcodes. We also perform a semantic comparison to make sure that the process hasn't inserted any errors. This is done by randomized differential testing against the original specification before all of this partial evaluation. We find that it does produce residual programs which are equivalent to the specification and equivalent to the original online lifter, modulo some syntactic differences. But we find that about 32% of the opcodes we looked at were in fact textually identical after variable renaming, which is good. And with this, we can obtain some bounds on the complexity based on the number of expressions in the offline versus online residuals. And we find that they are approximately the same, differing only about 10% more in the offline case, which is okay, but it could be improved further. We also looked briefly at verification performance. We tested this by feeding the results of the lifter into an analysis tool, Bazel, an in-development binary analysis tool. Briefly, this generates weakest precondition assertions, which are then passed to Boogie, which then uses Z-free. And we find that it does increase verification times slightly in the maximum, but not so much in the average case. And the resource count returned by Boogie is slightly increased as well. But that can be improved in future work. Okay, so in conclusion, we have developed this offline partial evaluation as an extension to ASLP. This generates standalone lifters from ARM's instruction set architecture semantics. It applies these opcode-sensitive analyses and transformations to further simplify the residuals and make it comparable to online partial evaluation. And it can be easily translated to arbitrary languages and intermediate representations, which we hope eases adoption in other analysis tools. For some future work, we will look at implementing further simplifications in the style of BDDs. We would like some more formal verification of the pipeline, such as by translation validation or emitting a proof. We are interested in deriving more useful tools from the architecture specification, and also exploring additional specifications such as the as yet unreleased Intel ASL specification. Okay, so thank you for your time. You can find some links here, as well as some suggested search terms, which should link you to the same pages. Thank you very much.
So can you comment on the sort of memory model that your system supports? I know ARM has a weak memory model. Is that captured by these semantics?
It does. It's a good question about the memory model. And unfortunately, that is not captured in the machine-readable specification which ARM gives us, because it's written in prose. So there's not much we can do about that, but that is of interest to our group. So we're thinking about how we can kind of layer rules on top of the results produced by this tool to implement a memory model.
Hey, thanks for the talk. I'm a bit interested in how something like thumb mode, like a decoding context, would affect like your lifting. Does it mean that you just have to permanently lift that as like it must be deferred to runtime? Because something like like a branch that like switches mode, etc. Like, is that just stored in the state and it's all runtime, or how does that end up happening in your offline optimizations?
Thank you for the question. So I assume you're referring to the different 32-bit modes which ARM can operate on. Briefly, the answer is we only handle the A64 mode. But yes, switching between modes at runtime is not something which we prioritize, I imagine, but what you would have to do currently is just run the offline process again with different assumptions to lock you into 32-bit mode or something else. Mm. So the question is it possible to implement in the current framework? One imagines you could simply add more state to the lifter, which would track this current mode. But yes, then it would lead to, as you said before, much more runtime branches for each encoding. And I'm not super sure, but in fact, I think the interpretation of opcodes changes based on which mode you're in. Which is, I don't know, it would push this kind of runtime stage all the way up, which is detrimental to verification. Yeah, so that's a good question. It was about how we would point to here, formal verification of the pipeline. Briefly, okay, so this is something which is enabled by the offline lifter in particular, which the online lifter would have had trouble doing. Our plan was to generate the offline lifter and then target something like Isabelle Hall, some kind of proof assistant language. And then we would reason with this against some other formal model theories in Isabelle, and then we would do something there to establish an equivalence.
Thank you. My question is a bit more strategic. So do you think that these machine-readable specifications are expressive enough that we have a chance in the near future to do something like software verification, but at the assembly level?
Yes, I do have hopes. At the moment, there are lots of groups working on formal specification of the architecture, and they're each approaching it from different directions. You asked about weak memory models before, and that exists in some axiomatization, but it's separate from what we look at here, which are the kind of operational semantics. But yeah, one hopes that one day this could be unified into something which could give you a sound decompiler, and then you could reason about assembly almost as easily as if it was a higher level code. But much more work to come. ARM and Intel are still working on their refinements to the ASL language, so it is an active area of research.
Okay, that ends the session. You can head to lunch.
Okay, so welcome. Detection for Go.
So it's my turn now. Who? Okay. Can you hear me well? So great. Oh, so it should be 16 to 9. Well, it's fine. It's 3 to 4. I think it's okay. Good afternoon, everyone. My name is Bojin Liu from Texas A&M Corpus Christi. We are another campus of the A&M system. And here I'm presenting this paper, right, GoGuard. Well, I think most of us, we are not strange to concurrency bugs, right? And Go, as a relatively new programming language, it introduced a lot of synchronization primitives, right? Makes developers' life easier and hard because it introduced new types of Go-specific bugs based on the fact that we already have a lot of traditional concurrency bugs we need to detect, we need to deal with, right? For example, I list some here. These are not the full list, just some classic examples. And later, Tool proposed a new classification for concurrency bugs in Go programs, right? They divided them into blocking bugs and non-blocking bugs, right? The blocking here means one or more Go routine, the execution is stuck and it cannot proceed anymore, right? So based on this classification, most of the recent research effort is put on this Go-specific blocking bugs. Most of the time, it's channel-caused blocking bugs, right? And meantime, existing classic works, they still works for detecting traditional concurrency bugs for Go programs. For example, is ABBA lock, double lock, right? The problem is because of this classification, the existing two groups of works, they separate. They have different emphasis on bug detection, so they can miss true bugs. Another reason is because the real world scenario, concurrency scenario is complex in real world programs, right? You can have channels, you can have logs everywhere. They somehow conspire to conceal each other, right? They are mixed together. It's not only channels or only deadlocks there, right? So the key demand here is we need something that can unite the communication behaviors of traditional concurrency bugs and Go-specific blocking bugs, right? So we can detect them together, both of the type of bugs together. And that is the motivation of GoGuard, right? It unites the presentation, the communication of Go's synchronization primitives. Well, here, these primitives include logs, mutex, channels, conditional variables, blah, 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 a lot of them. Well, GoGuard for now is implemented to detect blocking bugs, but it has the potential to detect non-blocking bugs as well. And we compared with the state-of-the-art tool Gcatch, and we have the similar performance based on the evaluation on the whole packages, and we can detect the 10 more true blocking bugs. These blocking bugs are coming from real-world large Go projects. So our tool is publicly available on GitHub here. So next, let's take a look why it works well on detecting blocking bugs, right? Including traditional blocking bugs and Go-specific blocking bugs, right? I think we are all familiar with this problem, right? Producer, consumer, right? Anybody don't know about it? Right. So the key thing here is we want to let producer produce pizzas all the time, put them in a shared buffer here, right? And producer and then consumer can take pizza out, right? So this flow can continue when we have pizza, which is this task or messages from producer, as well as we need to have consumer here, customers here, right? So anything missing will block this flow here, right? So this blocking, this concept here is really, it aligns really well with Go's synchronization communications, right? So for example, here on the left-hand side, we have this producer, we have a chef mouth, right? So we send pizza into this channel. And through this channel, we have two producer, right-hand side to eating the pizza, receive the messages, right? So here, the channel send operation works as a producer, and these two consumers are receiving messages here, right? So that is one example. And it also, this concept also goes well with the classic mutex, right? So when we have an unlock, we can see it as a producer, which released a lock object, and then this object can later be obtained by a lock from another thread, right? So here, the unlock here can be a producer, and the lock can be a consumer. So somehow we can map the Go's synchronization primitives, their statement, their creation, into this resource producer consumer relationship. Right here, we enclose this channel, mutex, context introduced by Go, wait group package, which works like this thread start and join. No start, just join. And sync new condition is the conditional variable in Go, right? So here enclosed most of the major Go synchronization primitives. And the resource here, we identify them as this object, like for example, the object of channel, the object of the locked variable, right? And we also identify the producer statement, for example, the channel send, and the consumer, like the channel receive, right? So these is somehow the foundation for the later we can detect the blocking bugs using this theory. And one thing good here is that this concept unites the traditional and Go-specific concurrency primitives and formulate their control flow into a single general form. Right, so we can leverage this to detect channel caused blocking bug and mutex caused blocking bug. And as we all know, statically, if we want to detect some bug, we need to know the happen before relationship among a multi-coroutine thread program, right? So we developed this resource flow graph, including two types of messages here. One is this producer-consumer relation we introduced in previous slides, as well as the static happens before relation, which is necessary to detecting bugs, right? So let's see a small example here. The code is a little, I tried. The code is a little tiny. Let me explain a little bit. So we have three coroutines. Main coroutine spawned two coroutine, and all the three coroutines communicate through channel and sync wait group. So here, right-hand side, we have this example RFG graph here, right? It includes the happen before relations, right? For example, the main coroutine spawns the Go1 and the Go2, two coroutines, and when they end, which indicated by the exit node. And meanwhile, we also include these channel send and receive operations from this program. Right, we create a node to represent them, as well as these weighted group nodes. Right, one thing to note that is defer wg.done works as thread join is always executed at the end of the coroutine. So instead of creating new node, we just use the exit of the coroutine to represent it. And continue. So how can we leverage such a graph to detect blocking bugs, right? The key insight here is a consumer always blocks the execution of a coroutine unless a producer from the same resource can match with it, right? This is really simple idea, and this somehow guides our tool. And during this detection process, we are maintaining a set which is called heap. It keeps track of the go routines that can happen in parallel. And one thing different from existing approaches is that instead of enumerate all possible go routines or possible producer-consumer pairs, we only choose a go routine randomly from the heap when there are more than one go routines that can happen in parallel. Yeah? Race?
On the random choice, is there some fairness hypothesis? Is it fair choice or
No, it's
unfair? You can choose always the same.
no, we'll not always choose there. Yeah, it's a fair, right? Right. Thank you for the question. And continue with the simple example. Let me explain how this ship works, right? So how we detect the blocking bugs. So we will traverse the graph starting from the beginning, the root node of the graph, which is main node, right? So before we traversal, the heap is an empty site. There's no go routine there. After we visit the main node, the heap will be updated to main, and continuously the next two node would be the go spawn statement, right? Go 1 and go 2, and then we update the heap to main go 1 and go 2. And for now, that's it. And then we continue the traversal along this age, right? Because we are going to stay in one go routine for now. And next we see this WG dot, my mouse is gone, WG wait node, right? This wait node in our concept, it's a consumer. Consumer needs to be matched with a producer, but for now we haven't seen any producer to match with this WG wait node. So we cannot proceed. So we'll pause our traversal for main routine here, and we'll come back later. And next, we're going to pick a routine from the heap to traverse again, right? So let's say we'll pick go 1 to do next, right? So we'll traverse go 1. And here we see this CH send at line 3, right? A channel send operation. It's a producer in our concept, right? So for a producer, we need to match with its consumer. So resource-wise, we have two consumers here, right? I use the orange node to highlight them, right? One is in Go routine 2, the other is in the main Go routine. So for now, only the one in Go routine 2, that is a correct match with this producer. So because only those Go 1 and Go 2, they can happen in parallel, indicated by the heap, right? And then we find a match, and then we can continue the traversal and reach the exit of the go routine 1. And we remove go 1 from the heap, right? We finish its visit. And continuously, we will pick the only one remaining go routine from the heap set, which is go 2. And we continue traversal. We see this CH receive at 7, right? It's a consumer in our concept, right? Since previously we already find its producer, it's matched, so there's no need to pause the traversal. Nothing will stop it, and we continue and timer. My? Okay, so it's my alarm. Sorry, I have another meeting scheduled. Sorry. So, and we continue and reach the end of the go routine 2, exit, and we remove go 2 from heap. Now we'll come back to the main go routine. We haven't finished its traversal, right? So we were stopped at this WG wait node, right? And it needs its producer. Who are their producer? Exit 1 and exit 2, right? Because they represent this deferred WG.done, right? It's a thread join, works like a thread join. So producer and consumers, they are matched. And then we can continue the traversal in main go routine. And here comes the problem. We see another consumer here, right? This consumer somehow, we have no more producer. We have no more channel send operations on the same resource. We cannot proceed anymore. So somehow this indicates there's something wrong with the program, and it blocks here. So we'll report this to the developers. This is the blocking bug. You need to handle it. Right? That is a simple example to explain the process. So for ship, there are advantages, right? We introduced this randomness, which is somehow very similar to the real world scenario, right? In real world distributed parallel programs, we have many random schedules, right? However, we also have disadvantages. The major one is they also add this random selection of go routines when we picked for traversal every time, right? So these randomness can cause false positives and false negatives because we didn't enumerate all possibilities here. However, we would like to argue that we can implement the shape to explore all possible concurrent routines and all possible matched producers and consumers here, which will make our tool sound. At least there will be no false negatives. False positives we cannot avoid for static analysis. That is our high level, our tool for detection. And instead of that, we also have many optimization and heuristics added. So all these optimizations and heuristics, we observe them from real world projects, right? So all these are here to fasten the process of detecting blocking bugs. We implement our techniques based on Go 1.17 and the Go tool, while we adopt the origin-sensitive pointer analysis for identifying the resource, right, matching the resources, right? So this is a pointer analysis that's Go routine sensitive. So it works better to identify channels, logs created in different Go routines. And we also compared our evaluation with GCatch, the state of the art. We have two sets of benchmarks. One is GoBench. It includes 66 blocking bugs extracted from real-world large Go projects. And also we evaluated some recent commit from real-world large Go projects. For example, gRPC, etcd, Istio, and Surfing. So here we report the evaluation on GoBench, right? So on the left-hand side, this table lists the benchmark set from GoBench, and highlighted two columns are the number of blocking bugs we detect by using GoGuard, our tool, and GCatch, right? The bug is reported in the form of true positives and total numbers of detected blocking bugs, right? So as you can see, our tool can detect 61 out of 66 bugs from the benchmark set. However, GCatch only can detect 10 out of them. While the time performance is also difference, right? GoGuard only use 35 milliseconds for this benchmark set, while GCatch needs a little longer. And we further distinguished what types of blocking bugs GoGuard and GCatch can detect, right? Which is listed on the right-hand side table, right? There are basically three types of blocking bugs: communicate-based, mixed, based, and resource-based deadlocks blocking bugs, right? So as we can see, GoGuard can work well. We can detect almost three types of those blocking bugs, right? Well, GCatch is designed to focus on communication and some mixed types of blocking bugs, but it's not that ideal. And we also evaluate our tool on real-world Go projects. And on the left-hand side, we report the numbers of detected blocking bugs for real-world programs. Right? GoGuard reports 12 true blocking bugs with 16 false positives, while GCatch found two true positives out of 14 reporting blocking bugs. So this is something we didn't expect also when we evaluated the program. And this also indicate the fact that we need some algorithm that can unite the detection of different types of blocking bugs. The classification somehow prevent us from finding true problems in the real world programs. And on the right hand side, we listed the statistics of this RFG graph we have when we evaluate the Go programs, right? As we can see, so many channels and logs interactive together in the program. Somehow it's necessary to consider them together. Here we report the performance of running GoGuard and the GCatch on real-world programs. So we report this in the form of average time versus maximum time. And here we compare the performance on the whole packages, right? Since GCatch will scan every packages in a project, will do the same. And well, we have some good and bad, but in general, our performance are on the same magnitude on average. So this presentation, I introduced this GoGuard tool, which includes these 3 things we developed, right? RFG graph, shapes, and some optimizations and heuristics. And this GoGuard is designed to detect the blocking bugs, for example, channel cost, ABBA deadlock, double log, mixed style of logs. And that are something we already explored. Next, we would like to do is to extend this concept on detecting non-blocking bugs. For example, data races, race conditions, those classic concurrency bugs, right? So that is all my presentation. Thank you, and welcome any questions. Yeah, we have this optimizations, right? Right. Yeah, so that's yeah, well, I try to keep everything simple, so oh, yeah, sure. So how we achieve this loop sensitive for Go routine is we have 2 parts, right? One part is pointer analysis. We identify the Go routines spawned inside the loop, so we will create 2 Go routines, 2 contexts for each Go routines. So then the channel objects, the logs, all the objects and variables created inside that Go routine will has its own label. Right, so that at that time, Go routines found inside a for loop, we can distinguish them. So that is one part how we handle for loop. And when we do the detection, it's the same. So we'll also, well, assume we have these 2 Go routines are spawned inside a for loop. We'll also, based on the information provided by pointer analysis, we will be able to distinguish there are 2 for loops, and we'll create 2 of these Go routine graphs inside our RFG. Could you please Yeah, that is true. Well, because here we have some handlings of that information, right? So most of time when each iteration, for the case you mentioned, it's like in a switch case. Yeah, yeah, we'll have a switch case, right? Yeah, yeah. So so for those cases, we'll enumerate this matching. We will have different state. We will store those state, pairing with different producers and consumers, and explore them later. Yeah, right. That is a really complex case, yes. Yeah.
Thank you for your talk. If I got it correctly, there are still a few blocking bugs that are not detected. And if I got it correctly, they are all inside Kubernetes, the Kubernetes example. Could you please go to that slide? So
Which one?
yeah, a bit further. No, in the other direction, I guess.
Huh? Go forward, backward?
Yeah, forward, please.
Here? No.
Yes. So here in the Kubernetes line, it seems that all of the blocking bugs that are missing are coming from the Kubernetes example. So yes.
This one?
Yes.
Uh-huh.
And I don't
Yeah.
know, is there some sort of specific
Well,
pattern or?
Yeah, no, that's because we have those random selected go routines, and sometimes we couldn't select the correct go routine, so it will miss the bug. That is how we have some missing here, right? We missed 5 of it here, right? But if we update the tool to enumerate all possible go routines, and instead of randomly selected, we can do that. But that would be very expensive because it would be large space to explore, right? We don't want to sacrifice that performance, so we picked this to implement, right?
Okay. Last question.
You showed the runtime for your tool, and you are doing the pointer analysis also. So is the runtime of pointer analysis included in that?
Right type of pointer analysis is another work published.
No, you are using origin sensitive pointer analysis, right?
Yeah, right.
So when you show the runtime of your tool like GoGuard, does it also include the runtime of computing the points to analysis, or it just uses the results as a client?
Yeah, it includes the time of running pointer analysis, and actually running pointer analysis takes a longer time, takes a large portion of the whole detection time, right?
Okay, yeah. Thank you.
You're welcome.
Okay. Let's thank the speaker again.
Thank you.
So the next and last speaker of SAS 2024 is Keisuke Nishimura. And the title is Should We Balance? That's the question. Toward formal verification of the Linux kernel scheduler. This neat paper.
Okay, so Okay. Hi everyone, I'm Keisuke Nishimura, and today I would like to talk about our work. Should we balance towards formal verification of the Linux kernel scheduler? This work is a verification of Linux kernel scheduler focusing on one function called should we balance over versions. This is joint work with Julia Lavoie and John Pierlotti. So let me start with the talk. Let me start with the background of this work. The Linux kernel is considered to be reliable, but the reality is not. It has a lot of bugs. Common bug patterns such as null pointer dereference or use after free. These bugs potentially can be detected by existing tools such as Coxnells or whatever static analyzer. But semantic bugs, violations of specifications, are hard to catch. So our ultimate goal is to address this issue by applying formal method to the Linux kernel. But without any supplies, verifying the Linux kernel is very hard. It's written in C with a lot of pointers and low-level features. Also, it's not designed for verification. And in addition to this inherent difficulty of the verification, the Linux kernel Linux kernel evolves rapidly. So which means that even if you verify the code in the kernel, the verified code can update frequently. So here's one research question comes up to us. Is it possible to port specifications and proofs for the formal method from one version to another according to the development of the Linux kernel? So we conducted a case study about the feasibility of porting specifications using one function in the kernel. We started by providing specifications for one function and proving the correctness. And then we tried to port specifications and proofs. Proof is, for example, proof is a loop invariant, for example. So we would like to see how reusable the specifications are and how hard to update specification according to the development. Our approach uses a deductive verifier called FRAMA-C, and here a specification is a combination of preconditions and post-conditions. We also focus on one function itself, and we provided the specification for queries without verification. Also, we ignored the concurrencies of the function and memory issues for simplicity. So the target function, we selected a function called should we balance. The function is in a scheduler of the Linux kernel, and this function decides if load balancing should be triggered on a given CPU or not. This function takes one CPU and its context as an argument and returns true or false. True means that a given CPU should do load balance. This function is introduced in 11 years ago and maintained with 11 versions. So before looking into the function itself, let's see how load balancing in the Linux kernel works. When there's at least one idle CPU among the CPU set we care about, the first idle CPU should be selected to do load balance. In this case, CPU1 is the first idle CPU here. This guy is the first idle CPU, and this CPU is selected and try to steal a task from the busiest one. Here CPU 0 is the busiest CPU. So the function should we balance returns true only for the CPU 1. For the others, the function returns false. And when there's no idle CPUs, then the first CPU is selected as a load balancer. And from the viewpoint of this function, only for the first CPU, this function returns true. So we can say, so we can model the function as a predicate that takes one CPU and returns true or false. And also we can see the two interesting properties. The one is uniqueness. This ensures that two CPUs try to do load balancing at the same time, because if it happens, it can cause lock contention in the busiest CPUs, so it can degrade performance. So we can write it down as a logic expression like this. If if should we balance of CPU 1 returns true, then the invocation of CPU 2, which is different from CPU 1, returns false. Also, at least one CPU should do the load balance. This is the properties of this function. And here's the brief history of should we balance. We can see 11 versions from starting 0. In this work, we first provide the specification of provide the specification for version 0 here, and try to port the specification again and again to version 10. And surprisingly, out of 11 implementations, 3 versions had a bug. We will revisit it later, and let's see the actual implementation of this function. Again, this function takes one CPU with its context. Here, it's packed into one structure called LB end. Also the target CPU, the given CPU is here, DST CPU. And we can see this iteration over CPUs. And if the CPU is the first idle, then the ID of the CPU is assigned to balance CPU here. And we'll exit this loop. If you cannot find an idle CPU, then the first CPU is assigned here. This function group balance CPU returns the first CPU. Finally, it checks if the given CPU is equal to the CPU should do balance. But actually, this is a bug, because as again, this function returns true if and only if the given CPU should do load balance. So in this case, we should check the equality of the. So we should check the equality. So the this fix was alive sooner. So the actual Linux release, the official release of the Linux kernel does not have this bug, but still this is in the Git history, the development history of the Linux kernel. Also, this is the specification we wrote for this function. We skipped some details, but we can see that here's the case where there is at least one idle CPU. If there's an idle CPU and the CPU idle is the idle, and there's no CPU, the CPU I is the first idle CPU, then we will check if the given CPU is equal to I. If there is no idle CPU, then we will check if the given CPU is equal to the first CPU returned from this group balance CPU. So let's move on to the porting part. Due to the time limitation, we skipped some version and focusing on some interesting cases. The first one is optimization. Optimization won't change the result of the function, but it should make the function faster. And here is the introduced patch. As you can see, return statement is in the loop, in the iteration, because we can make the decision when we find the first idle CPU in this loop. Yeah, so this is very concise but very good optimization. And for the optimization, we did not need to update our specification. So this, although this optimization changed the program structure, the control flow graph, for example. However, we didn't need to update the specifications, also the proofs, loop invariants. So we can say that certain performance improvement could be made without updating specifications. However, things changed when we update the algorithm. So let's see another case, algorithm change that can change the return, the result of the function. Again, this is the first algorithm, first implemented algorithm. The first idle CPU is selected as a load balancer. In this case, CPU 3. But in this implementation, one important hardware feature is not considered. It's called SMT, simultaneous multithreading. The SMT feature make a group of CPUs. In this case, it's called core, and here CPU 2 and CPU 3 belongs to the same CPU group, core 1. And core 1 has a task, and within that group, the CPU shares some computational resources. So which means that CPU 4 is more idle because the core 2 has no task. In the new algorithm, first idle and core idle CPU will be selected if available. This is a good change, good improvement of this function. And here's the code change. So as you can see, there is a check for the core idleness within the iteration over CPUs. We will revisit it later, so we won't go into the details of this algorithm implementation. But we found that this new algorithm forced us to work a lot to update the specification. In terms of the loop invariants, we needed to add a lot of cases to capture all information introduced. Also, the volume of specification became more than doubled, and so we needed to write a lot of new feature newly introduced by this algorithm. So finally, we will visit the most interest. We will visit the part of the bug we found. I like this section, but so again, this is the original implementation of the new algorithm. So let's look into the detail. So here, this is within the iteration of CPU. If the CPU is idle, but it's not co-idle, and it's the first idle CPU, but it's not co-idle, it's a bit complicated, then the CPU ID is assigned to idle SMT here, and checks if the idle SMT is equal to the given CPU, and if so, returns true. And also, if we reached here, we assume that there are no CPU idle CPUs, and returns the so we will check if the given CPU is equal to the first CPU. This is a bug actually. So let's consider this case, this simple case. Here there is no core idle CPU, but there is one CPU idle CPU. Here, this guy. We reach this if statement, and idle SMT points to this CPU. So here, from the viewpoint of the first CPU, this guy, this one returns true because idle SMT points to here, and we won't go into this if statement. So we reach here, and this is evaluated true for this first CPU. However, the third CPU, this CPU also returns true because it goes into this if statement. Actually, this is a violation of the uniqueness property I first introduced in this presentation. In this case, two CPUs can potentially try to steal a task from the busiest CPU, so it can cause lock contention, and which can cause performance degradation. So we should avoid this pattern. We proposed a fix, and we send it to the Linux kernel developers. Here's the proposed bug fix. We added a more precise check for the case of the case where there's no core idle, but there is idle CPUs. Actually this bug fix was approved and merged in the upstream, but we have not succeeded to verify the correctness of our proposal with regard to the uniqueness. So this remains future work. But anyway, we could find a real world semantic bug in the Linux kernel through the process of verification. So I'm very happy to achieve it. And I skipped some technical details in this presentation. Mainly, so we only visited 3 parts of the porting effort, but there are some more updates, and the paper described their effects on the specifications. Also, the paper evaluates the time required for the verification and some other statistics. From this case study of should we balance, we can learn something. the one is we could make performance improvement without updating specifications for optimizations, for example. On the other hand, when updating an algorithm, we needed to work a lot to update the specifications. And finally, even in the Linux kernel, bugs could be found, so we needed to work to identify such semantic bugs more and more. Of course, it's impossible to generalize our findings to any other functions in the kernel. It's a case studies for one function. And as a future work, we will try to verify the correctness of kernel functions and try to port their specifications. And also, as I said, we need to prove the uniqueness and existence properties for all versions of should we balance. And also, our ultimate goal is to automate this porting process, because it's very error-prone and tedious to port one specification to another version, and it's not widely acceptable among kernel developers, at least. So we try to improve this process more developer-friendly. So to conclude, we conducted a case study of verification for should we balance function over 11 versions. The key points we found were, the first one is we could make performance improvement without updating specification. On the other hand, we sometimes need to work a lot to update the specification in the case where an algorithm changed. And also, bugs could be found in the Linux kernel. We need to try to identify such bugs and make the Linux kernel reliable more and more. Actually, this is the last slide, and all specifications and the definitions of the should we balance are found on this Zendo link. Thank you for listening. I'll take any questions. Thank you. Yeah, we needed to try to write a specification and see if it's true or false. And also, pharmacy can take very long time to find it's the true or it becomes timeout. We set the timeout of 1,000 seconds. For the latest version, we needed to wait 14 minutes and to see if that's true.
You had to interact a lot with pharmacy, or was it fully automatic?
For the verification part, it's automatic. If the specification was correct, but if it failed, then we need to check the correctness of the specification. Actually, we focused on the Linux kernel scheduler, which is not a real-time scheduler, and certainly the the real-time scheduler has unique interesting properties to guarantees some timing constraints, but in our in our case studies we only focus on the not CFS recently, but the default scheduler, which is not a real-time scheduler. We ignored the about the concurrency in the specification.
So how does concurrency matter for Linux kernel schedulers? Nothing.
Nothing. So I think it becomes very difficult to verify because the concurrency, to my understanding, concurrency is related to very low primitives of the memory related memory instructions. So far, in theory, it might be possible to capture some kinds of concurrency issues, but still, I think it's a bit far from the from fully considered concurrency. To consider concurrency. It's far, I think.
Do you know if your correction of the bug improved the performance or worsened it, or you have some idea if it's better or worse?
Actually, we have not conducted the real-world evaluation of performance improvement.